Hi, welcome to Automat Live Coding. On this stream we are writing a desktop automation app, more of a game automation app called Automat, where you can combine all sorts of small devices together to do stuff on the desktop. Here we have a simple, this is the classical macro recording setup in Automat. We have a hotkey. A hotkey is connected to a switch. A switch switches on a macro recorder. A macro recorder records into a timeline, and there is a separate hotkey and switch that can activate the timeline. Timeline is connected to a bunch of objects which perform different actions. I was using this for doing macros in Kingdom Come Deliverance a couple of days ago, so those keys are the keys that are used in that game. And right now we are working on mouse traces. We are trying to improve those shapes so that this display, so that it's more readable, so it's clear what's happening with the mouse. I can actually play this, so when I play this, I will lift my hand out of the mouse, so you can see that the mouse is going to move by itself, right? This is the track which is recorded, it is being replayed here. So it did that, and now it does these 8 shapes. Right, and it's going to run in a loop because I looped it around. See, the end of the timeline is connected back to itself. It's very straightforward, really. It's kind of like programming, except you don't need text. You can connect objects to one another and they work together. Today we have some maybe a little bit too ambitious plans. So first I want to do some refactorings. I want to change the time representation that we have in Automat from doubles to 64-bit integers. Maybe I64. Yeah, I was wondering whether they should be unsigned or signed. I think signed, it limits our range a little bit, but we'll have to do some math to make this decision. I guess that signed is a little bit safer because we can create negative differences. And I mean, you can also do this with unsigned. But with signed numbers it makes sense. The compilers are not going to punish us for this. Point 2 is segment trees. So segment trees have been my weakness for years. I just didn't bother to learn them ever, because almost always you can find a better data structure that can solve the same problem faster. Like usually, like people, for example, say that you can use segment trees to compute subsums. You know, when you have a sequence of numbers and you want to compute a sum of a segment of those entries, segment trees are perfect for that. But I always preferred just sorted arrays. Sorted arrays take the same time to construct, and once you build them, they are even faster because they use less memory. And a single query on a sorted array is constant time, on segment tree is logarithmic. So I just never really was convinced about segment trees as a data structure. But after having fought with this display for a little bit, I think we can actually find use for them. Like the big advantage of segment tree is that you cannot really achieve using the other data structures is that you can do min and max queries. And when I was thinking about the proper way to draw those displays, the proper way to chunk this thing, I think the key is to identify the gaps and to put displays below the segments, but avoiding those huge gaps here. So this is what I would like to do today. Yesterday I've spent the whole day kind of working on a single segment tree implementation, and I think it's pretty decent right now. It definitely passes the quality bar that I want to have. We are going to just tweak it a little bit by adding C++ concepts. Because the segment tree should be configurable, it shouldn't be just a single tree. It's very easy to have the same type of tree for different data types. Not just numbers, but possibly images, other segment trees. Integers, doubles, integers of different sizes, doubles of different sizes, and for different search criteria. Then we will try to use this newly added segment tree to better chunk the timeline into more meaningful displays. I will explain what I mean. So you can see here, there is this blue section. This blue section is the movement of the mouse. So you can see this line here. This is probably the first vertical move. When I move you can see this hairline here. I just move it through this first section. So this first section is this first vertical move. Then there is the second vertical move, third, fourth, fifth, sixth. So what I would like to have is when I am unzoomed, I would like a single display to show those 6 movements. But when I zoom in, I want this to split into 6 separate displays, each of which will show only a specific part of the movement. And here you can see, for example, there is this last couple of pixels, literally, that are in the last display. So the chunking here is very uneven. I don't like that. I think we should come up with a better approach. The advantage of the current one is that it's stable. If I play it, it's not going to re-chunk the displays in any way. See, so they are staying attached to the time strip. This is a property that I would like to keep. I would like those displays to stay attached. So this is the plan for today, and there is one more extra. There are presentations from the Better Software Conference that I couldn't watch, that we can watch together now. If there is a break, we can watch this presentation by Casey Muratori. He's the author of Handmade Hero. This is an online, this is kind of like open game, like openly developed game, where everybody can watch how it's made. And this is why I say this is a very ambitious plan. We have a lot of things to do today, and I just took 2 vaccines at the same time, in both arms, so I may be a little bit tired. But the symptoms will kick in a few hours, so before that, we have time. Okay, let's start with changing time to 64-bit integer. I should probably stop Automat. Switch to cursor. Cursor really wants to update. I lost my trust in this application. I'm going to avoid updates as long as possible, and if they eventually force them, I may actually try switching to something else, like Z, maybe. Z sounds like a good alternative. Okay. This is my segment tree implementation. It's actually super compact if you ignore the comments, which there are a lot of. Can I fold this? No, I cannot. Yeah. So this is slightly different than most segment tree implementations, but I will explain it in a couple of moments after we switch the time representation to 64-bit integers. Okay, so with those integers, I wanted to check something. So we have 2 to the power either 64 minus 1. So this is the maximum unsigned integer. And if we decide for signed integers, then this is the maximum. And computers, I was checking this implementation. If you use the most accurate timers, they give you time in nanoseconds. A nanosecond is still quite a lot of time, because during a single nanosecond a computer can execute 4 instructions. So a single nanosecond is actually 4 CPU cycles. And CPUs count cycles, so they can fairly accurately give you time. When I ask the CPU for the current time, it does some math to give me proper answer. But I think counting time in cycles would probably be very CPU specific. It would even depend on the speed of the CPU that it currently executes at. So nanoseconds, we will use nanoseconds. And I want to see how long tracks can we have if we use this representation. So actually, I should write it differently. So this should give us the number of seconds that we can represent, which is decent. It's a decent number of seconds. Number of hours, days, and number of years. 300 years, approximately. Okay, this is good enough. I don't think any macro is going to take more than 300 years. Yeah, I don't have anything in the working directory. Perfect. So I need to do this now. And we are not going to store the time in full seconds. I will store the time using this ratio. Oops. Semicolon. Okay. If this works out of the box, I will be impressed by the C++ Chrono library, because under the hood, this is a massive change. It changes literally the part of the CPU which we used to keep track is now switched over to general purpose registers. We are not using the floating point anymore for that. We are using the general purpose. It's likely going to break, but let's see. Yes, there are many places where I use count, duration count. Oh yeah. So the thing is, this used to return seconds, and now, because we are using ratio, it will return milliseconds. Let me... Okay, bring this. This is what I wanted. Yeah.
Jackson, she says.
Hello.
Hey. Okay, so to finish this refactoring, I will have to do two things. First, I will have to fix all of the errors. There are quite a few of them. And two, I will have to go through all of those usages of the count function and fix them, because they all assume we're working with doubles. Maybe not here, but in animation... Oh, animation. This is going to be a pain. For concurrent queue, we don't need them.
What you coding?
Hey, this is... I just broke the compilation so I couldn't show you, but if you rewind the stream just a couple of minutes, it's on YouTube, it's on YouTube. On Twitch you cannot rewind, but on YouTube you can rewind streams. I give a demo at basically during the first minute of the stream. It's a macro application, like AutoHotkey. If you're familiar with AutoHotkey, this is something similar. This is also why timing is very important here. I was trying to do macros in Super Mario Bros. Initially, that was one of the first toy examples that I was trying to automate, like playing through the first level of Super Mario. And it was just incredibly hard to properly hit the timing requirements. A game which runs at 60 frames per second and really pays attention to what you're doing with, pressing and releasing buttons. It's very easy to desynchronize Mario. You literally miss input for like 1 millisecond, you just hit the input 1 millisecond too late, it arrives at the next frame, and Mario performs slightly different action now. We've put a lot of effort into proper replay of those events. And I would say right now it's pretty decent. I don't need any of those py files. Ignore py. Ignore third party. Ignore builds. Okay, looks a little bit better, just 68 results, and I see all of them will probably need fixing. This is life, I guess. Okay, what are the errors? Okay, so we are keeping track of the screen refresh rate. I'm a little bit confused. Now minus next frame, okay, count, that gives us unsigned integer. And the next frame is in the future. So this produces a negative number. We should be able to work with that. If I make it auto, I guess this will become looks good. So that should give us the number of nanoseconds times 60. We have a ceiling. It's probably unnecessary. Yeah, and also that probably should be floor. Okay, now we have a long here. Oh, I see. What was the intent? The intent was to divide this to get a reminder. It's not quite frame count. Because screen refresh rate is positive. Should divide this here and multiply it here. By the way, this power save, it's slightly buggy, but I'm not going to fix it right now. I don't think I need to cast it into a duration. Right? That should just work. Durations can be divided, right? I am a little bit concerned it may not be doing what I want it to do. Okay, it says disable if rep2 is duration. So I guess this should just divide the number by 60. I hope so. And I think the same here. I can probably skip this. I will just skip the parentheses. So now we are dividing the duration by 60. And then multiplying it by 60. We don't need any parentheses. Okay, screen refresh rate. I'm going to just bury myself if I do too many changes. So now, skip this as 60 seconds. So this is the number of periods. Should be able to multiply it again. Oh no, it's not seconds. I don't know. If it doesn't render, it's probably because of this file. Period. What do you mean? Cursor is trying to mess the code again. It wants to insert underscores here. They should not go here because this is part of the standard library. Standard library should not use underscores. Hey, Knight.
Sephabuk says.
Maybe I can do this. Range duration. Okay, we cannot cast from a double. By the way, I should disable this if I'm doing it here. I am definitely doing some floating point math here. This should stay the same. So this is some kind of scaling factor. I can convert from a double to integer. By multiplying this. Okay, so I just changed. This is fine, this is fine. The power save function and the timer. And I don't trust myself. I think I injected some new bugs here. Again. So we have a double. Tick count returns an integer. this needs to be a double. How do I... Somebody has to have encountered this before. Nope. Okay, so I am serializing time as double, but that should be fixable, I think. Okay, so those are, for example, timestamps that I use for the mouse position. Okay, I want to read these back as double, that's fine. Okay, I think this is the correct way to initialize double now. There has to be a better way. So this is the least destructive way of converting the double into an accurate 64-bit value. I first multiply it by the numerator, and here is 1. Weird. Okay, and that should be the opposite. So when I create a new duration, the constructor where is the duration constructor? Using here's one second. Here is how we construct it from non-floats. From other durations. Okay, so here's how I can specify the number of ticks. Yeah, so I need to provide a number of ticks. So multiply it by a huge number and divide it by this, which is 1 here.
If he just followed on Twitch.
Hey, thanks for the follow. Alright, alright.
Vivkai says,
Hey, how's it going?
I think we need the same cast here. Can I go to my time? Okay, here I can pass anything. I mean anything, double. I could make it a template, but there is no point making it a template. The point is we are converting from a time represented as double into time represented as our duration.
Is this a personal project?
It's more of an open source project, but I'm like developing most of it. I mean, me and some common stream dwellers. Seconds. I'm thinking about providing a different, maybe type. I could have something like that, where I just represent time as double. We can have something like defloat. That will take our float duration d. It doesn't have to be float duration, it can be chronoseconds, std chronoseconds. That should also work. Okay, this is almost always preferred. So I'm keeping both. Maybe I can use those new times elsewhere, yes. Actually, so I need to do something like times n here, but this times n is going to break everything. So this will give us a huge number, which we can scale, divide, blah blah blah, and then use it to construct a new duration again. No need to shift it. So this will happen in doubles, and then we convert back. Okay, this is good. And the same here. I can multiply this by just a new duration. It's going to be so broken. But I had to do this. If I pushed this in time more, it would just cause more and more problems. This is the right representation for time. Just nanoseconds. This is what computers report. This is what they like. Okay, next we have renderer. When it comes to those two, I think the point here, the point with D, D is always used in a floating point context. So that the D, I think, should stay floating point. And the same this, when I'm asking for how many seconds has passed, I'm usually not interested in nanoseconds. Yeah, that would be super confusing. That should be always double. No, it's still not great. But I can convert from nanoseconds to doubles using this. So average draw millis is, I guess, a float, yeah. So I could make it a float duration. Somehow it works. Okay. Not complaining. Okay, this is what I mean when I broke the power save function. I'm not sure it really does any power save. And this time here, yeah, we are not deserializing time properly. Or not rendering it properly. Expected and in integer, but not double token. Deserialize it to 60. Okay, let's first fix the console logging. I think that was here. Or not. Okay, yeah. This is what I mentioned. All of the places where we used .count, they need to be inspected. "68 places. Okay, let's go through them. Animation. It's weird that it works with so many bugs. Right? Yeah, animation is totally broken. Okay, instead of this DT, now we have this timer D. Maybe not, because each animated value, it tracks its own last tick separately, because sometimes those values are not animated together. We can always do this. I mean, I have to fix others. Okay, yes. Spring is going to do crazy things. I think here we are using spring. That's why it disappears. And that math that we used here, it was insane. No, we will do it differently. We will do it using this, using C++ magic. I think this is much cleaner in terms of the intent. We're taking two durations and we are asking how many seconds have passed, and it gives us a double. Do I need to check count here? I think those places actually count makes sense. Okay, next let's take care of the renderer, because it was causing some issues. Okay, so this here, this gives us a so. So-like function. I think we have something like that. It's called steady so. Okay, this will actually do the heavy math using integers. So it's not going to lose accuracy over time. This was actually another problem we had, so nice. Caused by doubles. Cool. I think duration has... We can find the Tron library. I think there was operator modulo. Yeah. Sweet. This is actually big because doubles, they had this issue where they started losing accuracy. And I think they lose accuracy fairly quickly. We have something like 50 something, right? Bits. How many do we have? 52? So this is the value. And if my PC has been running for, I don't know, a month, okay, they still have quite a lot of accuracy in them. Oh, maybe this is because I'm using floats in many places. Floats have something like 24, 23, but there is also this extra 1 bit distart, so it's more like 24. So after a month of running a PC, no uptime, we are counting the uptime, the floats have just 6 points for each second. So they would become very choppy. And I've seen this when doing animations. When my PC had uptime of like 2 weeks, it was still acceptable and it was getting worse and worse the longer the uptime. It's fixing the renderer. Okay, so this is 2 seconds. I wonder why it works here. This is a steady point. Steady point. Oh yeah, I need to do from seconds. It's to be what? It literally works here. Maybe those have to be durations. Okay, I just fixed the renderer, so I think those messages should be gone. Renderer and animation. Okay, that should be 4. What's the issue? Okay. So apparently the compiler doesn't tell me there is an error here because this template is not expanded. It should be fixed now. I really like integers. I like doing math on integers because they will not pull any tricks on me. They have full accuracy at all over its value domain. Okay, there is nothing here, which is nice. Okay, the timeline probably doesn't deserialize its data too well right now. Animation, was it fixed? Oh, it was not. I need to expect more instances of count. Let me check the timer. Okay, the timer has a lot of usages, 16. I think if we go through this, should be fine. Okay, grabbing by this doesn't really do much. Looks like it's working fine. Probably the math when I'm moving the pointer is broken. But still, I think this could be fixed. It's actually not that bad, I would say. I think if I take this away, still be fine, but n is a duration now. I think dividing time by time should remove the duration annotation. What's the point of having types if they cannot remove, if they cannot cancel each other? Okay, apparently it does cancel itself. This is going to be a fraction. Okay, now n is a double. Actually, yeah, I was thinking that the chrono library forgot to remove the seconds, but it does. If I divide seconds by seconds, it gives me a row number. Okay, look at that. Now I can move the mouse and it snaps to seconds. Cool. Still a lot places to fix. And this is why I said this simple change, changing time to I64, it may cost us a lot of time, but it's good and it's necessary. It should have happened a long time ago. I think if I was more, if I did more kind of planning, I could have anticipated that and avoided this whole mess. Okay, some some functions which I don't think we used. I probably wrote those functions before I started streaming. But fix this as well, why not? We want to remove as many counts as possible, because count means that we are peeking into the internal representation. And the point of our time HH is to not do that. Okay, this should help it a little bit more. Unfortunately, not enough, not yet. We're not far, just 10 more occurrences here. Let's continue, just a couple more. I see we are doing a lot of this divide by range duration. See, maybe this could return float duration always. Actually, I wonder, maybe I can, because I don't like this time, 2 seconds, you know, all over the place. maybe I could do this. Okay, I can do using, and that will give me the right constructors. What is the issue here? I cannot define 0 because okay, the is duration is something that I apparently have to. This is a type trait class. So this is the base template. By default, it returns false. Here is a specialization that everything that derives from duration is a duration. Maybe I need to make this public. Okay, and this is the stuff that I want to fix. I think it doesn't want to accept derived classes. Actually, no, I know what I can do. In my time, I can say that, hey, this is a template specialization. My ratio. Implicit instantiation here. Okay. Because I could extend the specialized class with some extra members. Unfortunately, it's not going to allow me to do this. I can only pass template parameters. Maybe I have more template parameters. No, I have just representation and periods. It's a very minimal class. Okay. Go back to this. Okay, just a couple more places to fix. Is this one here, which we can, I think, remove. Probably do it better now. Okay, when I do this multiplication, it says it cannot pass double. But at this what was my float duration? Defloat. I can do defloat. So this is gone. Two more places. So when saving, yes. I want to do this 2 seconds. Friends. Okay, those were all instances of count within timer object. Ideally, timer object should animate nicely, but maybe I need to work on animation a little bit more. We'll see. Moving. It's animating. Yes, can grab this. Okay, there was a problem here. I think. Is it negative? But it was negative. Cool. Cool. Okay, timeline. We will have to fix the timeline now. Timeline is generating this error and is in this red line as well. So let's try to fix that. Okay, we are returning max track length as IMT. This is now an integer, a very large integer. Maybe that should be a duration, actually. I want to just have as little types as possible. Issue now? Sure. Nice. I can just make the code simpler. Somehow it's correct. Okay, track timestamps. Yeah. We will hold them as duration from now on.
Rose Dev says,
Sup, bro? How's the progress for today?
Okay. We're doing something very necessary. It sets us back a little bit, but those things have to happen. Otherwise, the problems will just accumulate. It's not quite refactoring. It's addressing some technical issues that we accidentally introduced a long time ago. So we used to represent time as double, which led to from double/float. We used mix of double and float at different points in our code base. And it's generally fine, but double inside CPU is stored in a very specific kind of unit of the CPU. And this unit is very volatile. When you call a function, the contents of these floating point registers, it gets flashed all the time, and it had accuracy issues because the longer Automat runs, the lower the accuracy of the float time representation becomes. So now we're switching to integers, which should make it not lose accuracy, and it should make it use fast CPU registers for all math. Mostly. Okay, current position ratio. Okay. I guess I can remove this. But I don't want to divide it like that. I think this should be Start like that. Playback offset. Should be duration. Remove the count. Actually, it has a good effect on code quality, this refactoring. It's another thing I want to do, upper bound, lower bound. C++ for some reason decided to use the most esoteric name. This upper bound is used maybe by some mathematicians, but in the algorithm world, this is just called bisect. This is binary search, essentially. I don't know why they decided to use the most confusing name possible, but we need an alias for this. Let me leave a to-do. I don't know, maybe here. Now, CMP comparator needs to be different. Cool. Current offset, that should be a duration. We have set offset. Should also be a duration. Cool. Continuing. Should be auto. Okay, this is going to be interesting because we have a float. Float causes problems wherever it appears. I can multiply by float, yep. It's okay. remove some parentheses. Actually, this is a duration, so what I need to do is I need to defloat it. All of those functions should be static. If a function is not marked as static, it's going to be emitted into the binary as a symbol. I think we are using durations for time instead of time t. I think distance to seconds should be a duration. Because when I just track the units of those different things, different variables, it looks like it all would make sense if I just kept all of them as durations. Slurp. Okay, lerp works in floats. I should have my own lerp. This is a float, it's a valid float, but those two could be durations, this could be a duration. X would be a float, because X is a ratio. Sorry, X is a coordinate. And that would be a duration. I'm a little bit afraid I will cause too many issues. change this. Not super happy with this, but why fix something that's not broken? We have x at time. At time should be a duration, I think. For symmetry, let's do the same here. Yeah, it becomes pretty obvious that we should keep this at duration. That would work wonderfully here, because the units would cancel. Hey, we are using some guard values. Duration guard. Is there a better name for this? It could be called bad duration, special duration, duration guard, guard duration. No duration. Okay, instead of this, what? Possible to take this? Wow. I'm positively surprised by standard library. Oh yeah, should not be using this infinity. It should work. Okay, this is another example of this case that it could really be a duration. Have duration guard here. I'm going to do this. Okay, this is float. No, it's not. Now this is the only missing bit. I need to fix this lerp function. How do we lerp integers? Yeah, this is all working on floats. But it should be possible to lerp integers. Oh, a nice trick. A really nice trick, actually. So this is one way to do this lerping. Another way to do this lerping is this. I like this one better, honestly, the second one. I don't think we can do it here. Let's do it like that. I will get rid of my lerp. Actually, this looks like same thing. Okay, now I have t minus center t divided by distance to seconds. Yeah, and that should give a float naturally. Cool. Okay, more changes necessary. Okay, this one is going to be tricky. So I need to take the current time, divide this by this value. Okay, I think this is a place to use 2 seconds. Okay. But I want to defloat this whole thing. Ooh. So I am actually using this as not so much tick mult, but tick duration. Okay, let's continue. Snap to track has issues. Time attacks is some funky value. I wonder why I'm computing this denominator if I'm not using it here. It should be denominator. This order, it should work. So the denominator is in seconds. Distance to seconds, it's also in seconds. So this is unitless, and this is in seconds again. So scaling factor is actually a duration. should be a duration. And see, and it actually shows here, because here we are computing time. But taking this initial breach of the offset plus some numbers times this duration, which we should defloat. Okay, this applies to should be a duration. Splice will also take durations. It's only problematic because this will be a very large integer. So it may round down. Whenever I do division, I should make sure that the stuff on the right hand side is a floating point. Slowly getting there. Current offset. Okay, I think STD format should support kind of format FMT time. Okay, 0-2 is fine. Precision. Here we are rounding the time to milliseconds. This is the first step. The reason I'm doing this is that I guess it's better than it's probably better than what formatting library would do. I have better control here. But I need to rewrite all of those time formats. Looks good. And this also looks good. Okay, in this here I need time float. Float duration because I don't want to divide by large integer. So close to the end. This file was a mess. It's good we fixed it. See another division. Let me make it just odd duration. Cannot decide between float and double. Use float. Still so many issues. Okay, again, I'm using this to divide stuff. Okay, I can remove this count. Parentheses are not necessary. On add. Cool. And this pixel t is being, I see, added. If it's added, then it should be stored as regular duration.
TP Chica says,
Mr. Sir.
Hey, actually, I don't even need floor if I'm dividing by integer. Integer division can bite. It's very hard to say. There should be different symbols for integer division, like in Python, and floating point division. Then that would be clearer. Okay, this max track length should be kept as duration. Okay, it's float duration. So many errors. Okay, but I'm removing those count calls. That's a good signal. Now, and this is the part which was causing the error messages. Yes, good. Just 5 more errors. Yep. this float happens using doubles. Those are all doubles. Just one more error, and it should compile again. Sorry, what? Delta is a time value. What is it doing here? Okay, I guess this is what was causing the weird twisting. There was some weird behavior when splicing timeline. Oh, it should be gone. Micro recorder now needs to be fixed. Those were just two objects so far. Timeline should look better now. It should show proper track segments. Okay, this movement doesn't work. It seems I can grab by this track, it works. By this also works. Okay, this is a very specific issue, this where the bridge jumps from start to end. That means we have divide by an integer somewhere, and that should be replaced with divide by float. This is harder to track. I should have paid more attention when refactoring, because now I have to do some investigation in this truly massive code base. So So there should be a place where I'm drawing the bridge offset X. Yes, here it is. Max track length. Let me see if there are maybe more places where it's a problem. Okay, this is fine. This is a problem. Here I am doing this float duration specifically because I want to avoid the issue. Also float duration. So the bridge behaves better. Seems like I can drag it properly now. Oh, something crashed. Just printed max track length. I wanted to check this. Can drag here. And it should snap to tenths of a second. This snapping is wrong. It definitely snaps to something. Okay, dragging the bridge does not snap. No, now it snaps. Maybe at higher zoom level. Higher zoom level, fun things happen. This stops working. I cannot drag by this. I can still move the bridge. It's like I said, simple refactoring introduces so many issues. Is our profiler, profiler, timeline. Yeah, zoom. Well, now I guess we have snapping to full seconds. Now we have snapping to the timeline positions. Also be able to grab the bridge. Bridge seems to snap okay. At this zoom level, let's see at this. Should be no snapping here. Okay, now snapping is happening. Okay, so dragging the track doesn't snap at high zoom levels. Let me take a note. When I drag it here, this snapping works, okay. When I drag the bridge, snaps here. Yeah, and bridge also doesn't snap. And at very high zoom levels, it gets stuck. Seconds, it works. At 1 second, not so much. I will keep it around. Hopefully it will crash. I have this drag timeline action. This is what happens when I move the pointer. I bet we have some division here. Yes, denominator. It's not defloated. Scaling factor comes here. This can be float duration. And I haven't even started the stuff that I wanted to do today. I was hoping a little bit that this small fix will go faster. Okay, that is our now we should be able to move it much more. We just should be able to move it now. Okay, and it moves. Does it snap? Actually, yeah, it kind of does. Nice. And the bridge? The bridge also snaps. Cool. I have 33 more usages of count. Which are all wrong. They should all be replaced by 2 seconds. With this refresh state. So I'm passing some time. This should be steady point. Let's continue. So that was assembler. Next is hotkey. What is hotkey doing? Oh, this is the fire paint. I should reuse this shader and do something cool with it. I just want to get the number of seconds since the drawing started. Yeah, actually, yeah, that's a good idea. Maybe this spring towards should receive durations as well. Guess I can remove this. Because C++ should be able to compare two durations. We still have some time here. Current time. Yes, there is a dust animation, which I totally forgot, and apparently it's broken. In the splice action, you can see it's broken because, yeah, it wants to cut some totally random values of time. Cancel this. Okay, I see. So we say that we want 10 particles per second. We start with the floor, then we go 10 back. Okay. Okay, this place action is very broken. Okay, this function time at x, maybe this is the problematic function. This time at x is used in 7 places, in snap to track, I think this is... center T0. This is half of the ruler. Okay, in seconds. T1. I guess I will just have to log some values from here, figure out what's happening. Okay, there is definitely no snapping happening here. So this time at X must be wrong. Actually, it's looking good. Maybe the issue is in the drawing function. If there is a splice action, Yep, this seems to be wrong. What have I changed here? Oh yes. Yes, I am dividing. This is what I said before. I am dividing by a large integer, which rounds down. I could probably rewrite it somehow. Center T1. Probably inline this. Let me see if I can rewrite this function. Maybe avoid some of the unnecessary complexity. So T has to stay at this center T. I can inline it. I can also remove this D float. I don't know how this works. Anyway, center T1 definitely can be replaced. Center T0 is this. By 2. I still have this division by large number, so it's still going to fail. But this is what I think might be fixed. Oh, actually no, works fine now. Actually, no, not that great. When I grab this, it jumps to the right for some reason. It's offset by some number of pixels. make a mistake when inlining this stuff? Yeah, apparently yes. So let me try to inline this all again. Start with center key. It's already wrong. Oh yeah, sign. I mixed up the signs. Okay, that was silly. I think I can skip this D float. Nice. Okay, so what do we have here? We have division of this minus this minus this. I think I can remove this, so this will become plus. I will just run this again to see if I didn't broke anything. can move this outside of this division and remove the multiplication. And the same with this one. Current POS ratio is a float. I could subtract half from it. If I drop this, I think this would still be fine because this one forces float. So this division happens in floating point anyway. And there is actually a nice interpretation to this. So x at time. First, we are grabbing this ruler length, because at half ratio, we are in the half of the ruler. And this component offsets it by some amount. Fascinating. Such a simple formula. And it's a key to all of this time display. Current post ratio. I'm using this as a almost currency in this whole file. It's in the logic of this file. Okay, let's go back to finding and eliminating all instances of count. It's 26 more. Wow. Actually, I could use something different here. Time steady. So or not. This is a modulo. It's just meant to be cyclic. This is fine. Sometimes I want steady so using integers and sometimes doubles. Okay, I removed some counts, so it should be better. 22 more. Shouldn't care about this file. So strange. Renderer test, which probably doesn't work. Okay, 17 more results. Still a lot. Get lag. Interesting. Maybe I should store lag as a duration. Scrolling issues. Okay, this one is actually justified. I want to get this. The denominator is going to be... it's fine. Okay, now I will try to test as much as I can. The refactoring should be... not refactoring, this wasn't refactoring, but it should be complete now. So we should be able to finally switch to those things. Let me see, can I record macros? Oh. Can I play macros? Space is being pressed. Wait, that was the most... Okay, stop. That's enough. That was the most important part. Timer. Does timer work? Seems to work. I don't know, those values. Can I run this in a loop? Yep. Can I capture the window? Yes. Does the OCR work? It should work. Not really using anything. It even did recognize something here. Totally wrong, but it tried. It's Vov. Okay. That was a massive change. Honestly, I'm already satisfied. If I were to call this a day, that would be good. But we're going to do the main thing for today. The main thing for today is display allocation on the timeline. Okay. Actually, that change made me a little bit tired, so I will grab some food and we will watch some of the Casey's presentation. So, be right back. Okay, so let's go with the video. It's rather long. I'm not sure if we'll watch it till the end. Maybe we will try. But yeah, we'll see how it goes. Maybe I can put this on top, something like that. And then we can watch it while coding.
Welcoming the one,
Stop the music.
the only, the
Let's go.
irreplaceable Casey Muratori.
Okay. Way too big. Sam made it way too big. I feel like before we start, we should also thank Sam for putting this together. It's been a very long time since I've been really excited to give a talk, and a lot of that is because the speaker list of this talk of this conference is absolutely amazing, and I don't know. I'm really excited to be here, and I'm excited to give this talk, so I'm just going to jump right into it. So I would like to talk about something that happened in 1998 at a company called Looking Glass, which normally, like back in the day, contemporaneous with this, if I had said Looking Glass, everyone would know who they were, because they were an incredibly influential game company that did a lot of firsts in gaming. One of their games, Ultimate Underworld, started kind of the 3D revolution in PC gaming. And they were incredibly innovative company at the time. And a lot of people today, I mean, there's people in the audience here who weren't even born then, right? So a lot of people today might not know who they were, but they were incredibly important. And one of their games was called Thief: The Dark Project. And it's a franchise that lived on. It was one of the first sort of stealth action games. And it looks pretty primitive by today's standards, obviously, but this was an engine contemporaneous with things like Quake, for example. So this was sort of state of the art at the time. Now, I'm not going to talk about graphics because I'm not qualified to talk about graphics anyway. I'm not a graphics guy. What I want to talk about instead is how they modeled entities. And normally, the way you would do things in games at this time, and in fact, the way that Ultimate Underworld 1 and 2, and then later System Shock was another one of their games, the way that they did things was actually the way that me and, for example, Ryan Fleury, who's going to be interviewing me after, we would say that this is a good way to do things even today. They were sort of fat structs, if you will. They just put everything in one structure, and when you were going to do things like have different types of entities, really all you had was some kind of a type field in there, or flags or things like that that would let you know what you were supposed to do with it. But these were very, very limited resource times. I think the systems, you would expect to have something like 2 megabytes of memory or something total to run in. So you're talking about fixed blocks of small size, and everything has to work in that. So that's just what you did because that's what worked. And in this time frame, right, during the 80s and then later 90s when this game was made, this is the sort of thing that was in vogue in the architecture world. This has nothing to do with how they were doing things at Looking Glass. This is what we would kind of think of as a normal OOP programming model now, where you have a hierarchy of things. Like there's an entity class, and then you have an NPC and item subclass derived from it, and then things below that and so on. And that was not something that Looking Glass had ever really used in that lineage of games in their RPGs. And they decided not to go that route, even though that was sort of what was in vogue at the time. That was what was, you would have seen pushed if you were reading architecture things in Oops Law or the kinds of papers that would have been published on software architecture. So they did something very different. What they did is said, look, we want all of our systems to be the primary thing that we're going to think about. We want to think about physics and combat and those sorts of things, the same things that were in our fatty structs. When we do a more serious architecture here, we're going to do more architectural work, we want to put things in terms of their system, not in terms of the entity. And so what they did is they came up with a system where they would use an ID, like if I have a particular object that I'm trying to model in the world, one of these entities, I just have an ID for it, and it doesn't really have any data associated with it at all. It's kind of the polar opposite of a fat struct. So they would just say, we're going to use the IDs to represent things, and then the way that we form the entity's data is we just use that ID to look up into a system and say, what's the physics like for this thing? What's the combat like for this thing? This fuel system I have, I'm just imagining systems you might have in a game. And in so doing, in 1998, when they shipped Thief: The Dark Project, they shipped, to the best of my knowledge, the first instance of an actually commercially released entity component system. That's what we call it today, right? People call it this. This is now an in vogue architecture in much the way that those hierarchy kinds of architectures were in vogue at the time, and still to some extent are in today, but not necessarily in the game industry. So this was the first time I'm ever aware of anyone shipping this kind of model. And in fact, it's the first time I'm aware of anyone even talking about this kind of model. I'd never heard of it before. This was the first time. And there is a pretty interesting thing that you have to understand about this, and I know this may seem like beating a bit of a dead horse here, but those red lines that I've drawn there are basically encapsulation boundaries. And this is a very important theme throughout this talk. I just want to really make sure I hammer it home. Encapsulation boundaries are really what we care about when we're doing architecture. What we care about is where we make it difficult to access things and where we make it easy, right? And so what they chose to do that was very different than that sort of inheritance hierarchy model is they chose to draw the encapsulation boundaries around the systems. Now, this is very different because the traditional OOP model, right, is you draw the encapsulation boundaries around the objects. So the encapsulation boundary in a normal OOP-like hierarchy is I have whatever the object is, like a mech, and the encapsulation boundary is around all of the things that the mech knows about. But that's very different.
It's not quite like that. Even if in Java style object-oriented programming you usually have some kind of composition of objects. Like if you have this like Java style object, you usually put some kind of combat state into it. And this combat state obviously has access to combat state of other objects. So it's not quite like shown here.
It's about all of the things that are related to a system, not all the things that are related to a mech. Now, it's important to remember, this is not like not OOP. You could easily call this object-oriented programming. It still obeys a lot of the principles you might recognize from object-oriented programming. So it's not like they were saying, we're getting rid of object-oriented programming. They were saying something very different. And they were saying, effectively, what Mark Blank said, he's the person who actually implemented a lot of the system. And what he said was, for some reason, OOP has gotten into this mindset of compile time hierarchies that match the domain model. Meaning, if you think about what you're trying to model in the real world, like entities and guards and things like this, or even if you're just thinking like the natural world, we're going to think about.
This is very true, and this is what also led to a distinction between object-oriented programming and object-oriented modeling. Because this modeling, it's a rabbit hole that often leads you astray, that forces you to try to model real-world entities as programming entities, which is not the goal to a working, not the right way to a working solution. It's possible to use object-oriented programming in a sane way, but instead of modeling the world, the objects have to map to components of the solution, not, real-world entities.
About, birds, and are they, is it a mammal or is it an avian thing, right? You're thinking about this domain model that you're trying to model in the real world, and you're bringing it into the software world. And what he was basically saying is like, why are we pushing this? Why is that the idea, right? And he says we can still do OOP-style stuff, and we can just do it by changing our paradigm of what we're thinking about in terms of our domain model, right? Don't make the domain model be in the code. Make that be something the user experiences, but the code is done in a way that makes sense for the code. So this is really brilliant, and it's a great way to summarize it.
But I have to say, this object-oriented modeling that he's presenting, it's a complete strawman. Like, when somebody does it like that, they are immediately scolded that this is the wrong way to do object-oriented programming. Everybody who does OOP knows that you just do not model entities as objects. You have to first think about how the data flows through your program and divide this data flow into objects. So the objects are not, for example, NPCs, individual NPCs, although they are also objects to some degree. But the different components of the solution, for example, on a Tetris board, right, when there are those Tetris pieces moving down, probably a single block in a Tetris game is not an object because of how it interacts with other things around it. Probably the right way to think about this is some kind of ground, and which contains some of the existing objects and maybe some, I don't know. It's probably the whole Tetris game could be a single object. It's not that complex, really. Object-oriented is really necessary when when the complexity of the simulation grows. And that criticism of the object-oriented programming, it's a complete straw man. It's nobody does it like that.
It's one of my favorite crystallizations of that concept. So I would only add one thing to it, and that's that word encapsulation, because I think sometimes people think hierarchy, they just think the relationships. But it's the encapsulation that's really important, because that's what really determines whether or not the code is easy to write or hard to write. Are those boundaries in the right place? So this is crucial. And this talk is kind of about mistakes, as you'll see. And I made a mistake one time. I went on this thing, you may have seen it, it's called the internet. It's like this series of tubes that connects people around the world, and it's kind of complicated, not 100% sure how it works, but they have a thing on it called social media where what you can do is there's like a box, and you can type anything you want into the box. It doesn't have to be correct, it doesn't have to be coherent, it certainly doesn't have to be polite. And then you have to push this button, there's usually a button next to it, but the button says different things sometimes. You push the button, and everyone in the world has to read it, like everybody. And that's an amazing invention. I was probably doing something like that at the time when I saw some people talking, having a discussion about this sort of thing, discussion in quotes, let's say. And they were thinking about this. They were thinking about, we have old things that were like maybe not quite architecture, like those fatty structs things. And at some point, people started saying, there's this other architecture we could do, which is this hierarchy thing, and that's like much cleaner. It's much better organized. It's better architecture. And they started to push this, right? And it definitely got adopted. It got adopted everywhere. And it's a very standard paradigm even to this day. And they were sort of responding to people who were saying this is bad, that this hierarchical thing is not a good idea. The encapsulation boundaries are in the wrong place, as I would say. And they're saying, okay, there's no way that all of these smart people who pushed this stuff and who created this, there's no way they could possibly be wrong about it, right? Like, surely this comes from all kinds of like academic studies and ways of looking at things, and we definitely have great examples of this working perfectly, I'm sure, and it all got translated to us, and you guys just don't understand, and we don't understand either because we're not really sure what we're saying, but we're basically saying that someone must have known, and those people were smart, so there you go, right? So could you really be saying, all you naysayers, that it doesn't make sense, and it didn't come from a logical place? And so the short answer to that is absolutely that's what we're saying. That's 100% what we're saying. And the long answer to this is the rest of this talk. Welcome to the Better Software Conference, the inaugural Better Software Conference. This is the Big Oops, which is my sort of attempt to go back over 35 years of history to figure out where we went wrong. Like, how did this happen, okay? Now, just get some things out of the way first. And this is mostly for the people. I don't know where I'm looking. Is there a camera out there? This is mostly for the people. The people in this room are probably already bought in, right? Low-level programming, that sort of thing. You're probably like, okay, I like where this is going. People on the internet, as I said before, maybe that was a mistake, but they're going to have some issues with this. There's some bones to pick. So I just want to say...
So there is a storytelling aspect here that obfuscates like the reality of things a little bit. It's like quite often those discussions, they are presented as dichotomy between object-oriented programming and some other approach, being functional, data-oriented, aspect-oriented, whatever. Objects, really, the reason that we are using them is that when we perceive reality, this is how we perceive it. Like, in reality, philosophically speaking, objects do not exist. Objects are just our mental devices that we are using to divide reality into meaningful components. If you look at this notebook, right? I have a notebook. It's a single object, but if I tear some pages out of it, you will suddenly recognize additional objects. Objects are just our kind of how we divide reality. The roots of object-oriented programming are not in some 80s, 70s, 60s computer science. It's in evolution, partially. It's in how our thoughts and how our language works. Our thoughts are strongly related to how our language works. So this is like one of the reasons. And in our language, you can see that there are nouns, verbs, adjectives, and a couple other types of speech particles. And because of the way we speak, we also perceive reality in a very specific way. And there are some very narrow interpretations of what object-oriented means. It's not what it really means. Like, really, it's about trying to understand some problem and trying to create a problem that maps your understanding of the problem. So in this view, like, objects are just something that corresponds to our thoughts. In this view, entities in an entity component system, like entities, components, and systems from ECS, they are also objects. They are just different way of viewing the same problem, different way of dividing it. I think what Casey criticizes this, first of all, this silly idea of modeling real world as objects, which it was a thing, but nobody serious was doing that. It was mostly, say, people who were just trying crazy things, trying something new, extreme, and it didn't work, right? Coq is a very nice example of this. That was a very old approach of artificial intelligence. It was trying to model real world as entities, like using formal logic. Of course, it didn't work because reality doesn't conform to those elegant divisions. So, in terms of object-orientedness, object-orientedness is really about dividing something complex into parts that can be easier to understand. And in this view, almost all programming approaches, except maybe machine learning, almost all programming approaches are object-oriented because they try to somehow translate our thoughts into the structure of the program. Some definitions of object-orientedness, especially the ones based on Smalltalk, they focus on the message passing aspect and encapsulation aspect. And maybe there are some also, if you know Uncle Bob's solid principles, like this kind of Java-style programming, it also developed its own approach to object-orientedness. It works if you know how to use it well. It's easy to abuse it. So I think Casey focuses on the abusers too much. Anyway, back to presentation.
First, when I say the big oops anatomy of a 35-year mistake, I'm not necessarily talking about OOP as a whole. I'm talking about looking for very specific things in it, okay? And because whenever you talk about OOP, it's always this thing where you're like, well, whatever you're talking about, like, that's not really OOP. Like, you're talking about the things, you're using the terminology wrong, or that's not how I write code. It's like OOP is...
This is what I'm saying. Like, OOP is a very, very general term. Almost anything. Like, almost anything where you can distinguish objects and their relationships and interactions with one another is OOP. So it's more like playing a language game at this point. It's hard to even argue for or against it because it's so fuzzy. There are just some specifications of OOP that you can argue with, not OOP in general.
It's just a thing where it's like, it's how I...
Actually, I keep saying OOP because he's saying OOP. This is OOP. OOP.
like to write code, and whatever they're thinking at the time, that's what OOP is or something. And I don't necessarily blame them because it's a nebulous term and they have their own definition for it. I mean, I probably have my own definition for it. That's totally fair, right? But I just want to say we're not going to be dealing with any of that here, so I don't want to hear the whole, like, I don't know. It's sort of like wine, which I got the slide up in here. It's like, if you have like a designated origin, you're not allowed to call it certain things, and it's like, it's that kind of feel, right? It's not like...
I think it would be worthwhile if he, there is this school of debating where you try to misrepresent the position of your opponent and then criticize it. I don't think that's a good approach. But, you know, discussion. I think it's good to present the arguments of the other side in the best possible light, because there are usually flaws there. Like, even if you present them in the best possible light, you can always find something, some crack in this, in the argument. Yeah, so just skipping this aspect, I mean, that's a negative point from me.
It's like, it's not actually OOP, it's sparkling code or something like this. You have to use the right term for it. So I just want to be clear, I'm talking about something very specific, and it's the thing that I just said. Very, very specific. And I'm not saying OOP was a mistake, I'm saying this was a mistake. The idea that you're going to draw encapsulation boundaries around these compile time hierarchies that are based off of whatever you're trying to write.
I take back my negative point. My negative point was that instead of having a precise definition that he can criticize, he said, I'm not going to delve into this, but then he showed the precise definition, so it's there. Okay, thank you.
Now, second thing we want to get clear is I don't want to hear any complaints that no one ever pushed this model, because I know that's going to happen. I'm looking at you, Y Combinator. I know that this is going to be a thread. So, anticipating that, let's just say we have a lot of historical evidence. When I was doing the research for this talk, I read so many things from the historical record. It is so obvious that everyone actually 100% meant you should look at the domain model and you should code that directly into compiled hierarchy. For example, here is literally Bjarne Strustrup's paper, What is Object-Oriented Programming? To tell you what it is. And he starts off with the shape example that I've used before that everyone said, well, that's totally ridiculous. You're just cherry picking out of an introductory book. It's like, this is where he was trying to explain this and sell this to people in his industry who were experts. And he says, look, if we're going to write something like this that has, you know, kind K as an enumerant there of like what the kinds of shapes are, right? If we're going to write something like this, we end up with code that has a switch statement in it. So when we want to draw something, we have to say, oh, what is this? And I have to say, okay, case circle, case triangle, and have the different drawings for that. And he's like, this is a mess. You can never do something like that. Instead, what you want to do is make a hierarchy where it matches the domain model. I've got a shape class, and then he derives from it the triangle class, and has a virtual function, and all those sorts of things. This is right in the first papers where people are selling this concept in certain programming languages, right? And I guess I should also point out that he says things like, when we're talking about object-oriented programming, literally what we're talking about is inheritance hierarchies with virtual function calls. Like, he says that, and he says object-oriented programming is programming using inheritance. So hammering home that this is literally what we are talking about. There's so much evidence, and I'm just picking one paper. Now, a lot of people will talk about, say, Alan Kay, because he was a big father of object-oriented programming. He's the one who coined the term, as far as anyone knows. And he talks about, you know, this sort of idea that OOP
messaging
only
aspect.
means like messaging and a few other things, right? He said this. And so some people might be like, well, that's what object-oriented programming was really about. No one was ever pushing it. And you know,
And messaging is actually totally irrelevant to this. Messaging was probably born out of some problem that they had at Apple or Park early on, because they had multiple different machines. They probably used different formats of code. And they probably, to interoperate, had to send some messages between one another. So it was probably very convenient to them to embed messaging as something fundamental to their object-orientedness. But it's like, modern computers don't work like that. Modern computers, they have CPU, which executes code, and then it passes control to another piece of code. It's about having the CPU jump into your own code or jump to the code that you want to invoke. And the coordination between objects is about organizing this whole affair. Like, whether we want to talk through a stack, or whether we want to, like, stack-based, like this is function calling, or whether we want to go through a queue, and queue is a message passing approach. Or maybe we want to go from some priority queue or some fancy data structure. The messaging is totally orthogonal to everything. Alan Kay also talked about encapsulation. A lot of people talk about encapsulation, that this is the defining factor in object-oriented programming. I'm not sure I agree. I actually think that the less the encapsulation is, the more flexible the code base is. It's a little bit... I think this whole encapsulation thing came from team structure. You know, when you have a team, a group of people working on some problem, they will often step on each other's toes, trying to, you know, achieve at the same goal, and they may break the code that belonged to another person. And when I watched some presentations from Alan Kay from early days, 80 something, he did some presentations then. They are recorded and on YouTube. It sounds to me like he had to deal with very careless programmers, and the encapsulation was actually a mechanism of damage control, so that somebody who just breaks the code all the time doesn't have the ability to break the key, you know, the code that he wrote, the important stuff.
Wantoninity 8 says.
Interesting things, TBH. I didn't watch the conference before.
Yeah, Better Software Conference. It was good. Other talks were also good. Like, some of them were excellent. Let's see. Okay, they didn't publish all of them yet, apparently. There is just one, but the next ones should come in the coming days.
CP Chica says.
Any new bugs today?
I hope not.
Bjarne Strustrup, okay, whatever, C++, it's terrible. Like, don't listen to that guy, right? Despite the fact that he made the language that's like one of the most prevalent. It's the one that we all use mostly, or at least have for the past 20 years. And so this is the truth. This is the actual truth here. It's like, yeah, he said that in 2003, right? He said that after a very long time. So why did he say it? It's because 10 years earlier, he was already saying he kind of soured on it. He's like, inheritance was like really powerful,
Speaking
but
of
people just didn't
bugs,
know how
one
to use
just
it.
flew in my
Novices
room.
and experts apparently both couldn't use it, right? It was just, you know, it's really good, but no one can figure out how to use it, I guess. So that's a little...
I had a friend who had a ferret, you know, this small weaselly animal. Once we came to his house, and it was smelling like something burned, you know. We found the ferret inside the PC case. It was alive, it was fine. It was just hanging on its leash because it entered the PC case somehow. It was open. It entered the PC case and the leash got into the fan of the CPU. So the ferret got stuck, the CPU cooler stopped working, and the computer, it was early 2000s. The computers didn't have particularly good temperature protections back then. And the computer just destroyed itself from overheating. Yeah, ferrets are fun animals. I love them.
Little bit weird, I don't know. Maybe Alan Kay, he
Matt
still
Hill
comments on
said.
stuff. Maybe he'll come and tell us what he actually was trying to say there exactly. But if you go back earlier, because small talk is a lot earlier than that, if you go back and look at what they were actually talking about when they were talking about small talk, in the times before they had a chance to reflect and say that it didn't work, well, here's what they were saying. Inheritance programming shows the power of differential description, right? They're like, you can take an object, and I can say, like, I'm going to start with this completely undifferentiated object, and then I'm going to derive a rectangle. I'm going to drive. And in fact, here's a diagram from one of his articles talking
CP
about
Chica
like cool things
says,
computer
That's
architecture is
probably
like,
first
we can
and
have
only
a
CA
dirt object,
affair
and
that
then we can drive
induced
another rectangle,
overheating.
and we'll drive a window, and a paned window, and a browser. Look, everyone is talking about literally representing in the hierarchy what your domain model is. That's what they're talking about. And if you need further proof, look at what's actually in Smalltalk. We have all the data, like for this, all of the papers exist. Here is an example from the art and science of Smalltalk where they're talking about some stuff that's needed to adapt values. Like I want to convert values between things and actually exchange values between objects and stuff like this. And here's just a hierarchy that they drew of stuff that they were using for implementation. That's the hierarchy, right? And if you look, it actually says, well, it's only part of the hierarchy for this thing, because, like, we couldn't fit it on the diagram. We had so many classes we were inheriting here, right? And guess what? If you liked the shape example that keeps coming up, that everyone says, well, no one would ever actually suggest that you use this sort of ridiculous shape example. You're just cherry picking, except it exists absolutely everywhere. It's in Smalltalk. there it is. They have a path class, and from that path class, they have different shapes derived from it. That's what the path looks like. That's in the base language of Smalltalk.
Those class hierarchies, they haven't been discovered, introduced for the purpose of object-oriented programming. Those come from ancient times. These are ontologies. I think Aristotle even wrote about them. Ontologies, there are those, should be some examples, yeah. Literally, the reason that those ancient philosophers discovered ontologies is not because they invented them. This is literally because of how we think about reality. We tend to categorize things into kinds or superkinds, and this is how we can generalize knowledge, you know.
Isn't Lua also from same era of Oops?
Simachil says.
The man mission is to take up down at all costs.
Yeah, but he defined the problem, like he has an enemy, and his enemy is representing domain objects as objects in a program, which is obviously a terrible idea. There are infinite, there is, in almost any domain, there is an infinite number of objects. In chess, you know, it's like you would try to represent each potential state of a chessboard as a separate object. And to some degree, it makes sense to do this, but when you are processing a lot of them, like, you often want to represent them in some more coarse way. For example, all boards where this piece is on this position and other pieces can be wherever. I haven't seen any nice picture, but ontologies, like the object-oriented hierarchies, have their root in ontologies. And the fact that objects don't make sense in the physical world is quite evident by many philosophical experiments that you can do. There is this ship of Theseus, I think that's the proper pronunciation. There is the teleportation problem. Like, those are philosophical problems, totally abstract, but they apply to this notion of objects.
CP Chica says.
It makes sense to that only if there are no branches after move. In going over 1043 possible states to actually not going.
Yeah.
Alan Kay and Robson Shipped and Adele Goldberg was first.
And honestly, this example from Smalltalk probably, it kind of makes sense. I mean, this is how HTML still represents. This is how SVG represents SVGs. It's convenient to have this object-oriented view of an image. It breaks down when you have too many objects, right? This is when you have to stop. But I think in the context of Smalltalk, totally makes sense. It's totally fine.
Who documented it. These are the original authors of Smalltalk, right? And if you don't want to take my word for all of that, you can take Bjarne's word for it. He criticizes Smalltalk for being all about inheritance, that's all it was, and you had to actually use it to get anything done in that language, right? And he's actually saying C++ at least doesn't make you do it that way. You only have to do it that way when you think it's a good idea, right? Which, by the way, I agree with him on that. That's why we were able to, that's why I'm still able to use C++ to this day, is because Bjarne Stroustrup was actually really smart about a lot of things, and he didn't try to force you to do things only his way, whereas Smalltalk kind of did. All right, so now that we've got that out of the way, let's talk about the origin story for this guy right here, who has caused me so much pain. And so, you know what, I won't even go into it. Anyway, let's talk about the origin story. So we'll start with C++, because obviously that's the most impactful language that really promulgated this inheritance hierarchy concept out to the world in a way that we all kind of experienced. Not only in programming C++, but obviously languages like Java, which are incredibly prevalent in not exactly our circles maybe, but obviously in business world and that sort of thing. So it's not even just C++. It's like the knock-on effects of C++ also. So this is really, really important as an entry into where this came from. So let's start in 1978 and looking at that. And Bjarne Stroustrup is actually in the, he's in university at this point. He hasn't actually gotten to Bell Laboratories where he would do the later work on C++. So he is working on his PhD thesis. And again, as I'm going through the historical record here, I really want to try and give you a mindset of what the people were thinking as far as I could get it from their writings, right? I went only through primary sources for this, and I tried to figure out what were these people feeling, like what were they doing when they were coding. And so he is actually working on distributed systems. He's not a languages guy. He's not there like researching language things like that. He's working on distributed systems, and what he wants to know is, look, we've got some stuff where we want to know about hardware protection, like, you know, if you kind of think of virtual memory or things like that, where you have hardware features that are designed to protect different parts of your program from other different parts of your program, or different processes from each other, or different nodes in a system, all those sorts of things. So he's doing distributed architecture work. And what he wants to do is run simulations, because at the time, again, putting you in the mindset of where we are in computer history, you don't just have computers lying around like we do today, right? It's not like, oh, I can just buy a bunch of computers and set up a network and do testing.
Simatil
No.
says.
There's no way he was going to get things like a distributed multiprocessor system to just play around on in 1978 unless he was extremely important and working for the military or something like that, right? So what he had to do was write a simulator. And what he decided to do to write the simulator, because earlier in his career, he'd been in university, I guess earlier in his education, I should say, he had been at university.
Sorry for the excessive loudness. Keys are super loud. Just change my keyboard or something. It's incredibly loud. Simulations are where objects really shine, because they allow you to really capture different behavior of different components of the system and still let them interact with one another.
And he learned from a person named Kristen Nygaard, who is actually one of the creators of Simula. He learned the language Simula directly from one of its authors, basically. Like he was actually there at the time when the author was also there, and this was how he knew what Simula was and how to use it. And so what he did was he wrote a simulator for distributed systems in Simula, which is kind of exactly what it's designed for, right? It's a simulation language. And he had a great time doing it. He was like, this was so much better than what I'm used to. I really liked the experience of writing that. So he ended up with this thing where he had like little programs that were simulating what was happening in a distributed network, or distributed system, I should say, not necessarily on a network. And he found that it was really easy to debug the little programs by themselves, and the language made it really easy to do that. Now, again, it's important to remember keeping all this in your head if you can. I know it's a lot. It was a lot of reading, right? So I'm trying to convey it to you in as close as possible. Just pointing out, it's important to remember that that's the domain model he was working with, is lots of little programs that were talking to each other, right? So anyway, he says that the class concept that Simula had, because it had the same sort of idea of a class as C++ would later have, he said that that class concept that Simula had was really good for direct mapping, right? Remember I said compile time hierarchy that exactly models the domain, right? He said that was working really well when he was implementing it. He was just saying, oh, this is the thing I'm...
So sometimes So the proper way to use OO is not to model the domain, but to model the solution, right? Sometimes the solution has objects, and then, yeah, it makes sense to model them. If he's doing simulations probably have a lot of interacting objects. It makes sense to model them as objects. Smalltalk had, at least the display of the Smalltalk language, had a graphical layer which had those objects. Therefore, it made sense to model them as objects. Doesn't always make sense. Some accounting software would be terrible to work if somebody tried to model, I don't know, numbers, values as OO objects.
Trying to simulate, and so I'm literally going to create classes in Simula that model that directly, and that was working really well for him in Simula. And you know, we can kind of start to see how this is breaking down. he happens to be working on something that is literally a domain model of things that are encapsulated. The computers can't talk to each other. The different processes in the computer can't talk to each other. It's an exact fit for what a class actually does. This is important to remember. Okay, so we used hierarchies for this, right? They weren't necessarily particularly deep, but they were the kind of thing where it's like, I have a computer, I derive different things from the computer, and those things are just kind of self-contained. And he had a really great time doing this. Again, he said very positive things about it. And one of the things that he really liked was the fact that the type system, when you had these hierarchies, that type system would catch errors for you. Exactly the kind of thing that we maybe take for granted today, because most languages, even JavaScript now has like TypeScript, right? Most things that we work with today have the ability for you to do this kind of type checking that catches a lot of errors at compile time. That was relatively new at the time. And I don't mean new in the terms of like no one had ever thought about it before, but I just mean a lot of languages you might be using at this time still have very weak type
code
systems.
alert.
And in fact,
I just got
Struster
Vulkan
complains
swap chains
directly
for
when
those
we
who are
talk about this,
ill-informed, the
that
part
using
where
Pascal
Vulkan code becomes messy.
I would be interested. So the way I'm setting my swap chains is it's pretty much based on some unit tests from Skia, which is probably not the optimal way to set those swap chains. It works. I mean, Automat somehow renders. But I would love to know how to do this properly. I even got a book about Vulkan to learn how to do it finally. I just haven't yet gotten to the part on swap chains.
Kind of sucked, and he didn't really like it because the type system didn't work very well for expressing things and for catching errors. He felt it was kind of more trouble than it was worth. So that...
By the way, I muted the TTS so that it doesn't interact with the video too much.
Forms his basis for this idea that classes are really good and type checking on classes is really good, right? And, you know, just to split those down the middle, I do think the type checking part's pretty good. It's maybe the class part, or rather the hierarchy part, that I'm like a little bit suspicious of, right? But at least half of it I'm with him on already, even. Okay, so that's sort of what you will see if you read the Wikipedia or something, right? That's the simple part, and they often leave a lot of stuff out. So I thought, because this is the Better Software Conference, I would include a much more interesting aspect of the story, because you would think, if you saw a thing that's like, hey, what happened was Bjarne Strustrup was doing stuff with distributed systems, and he wrote this thing in Simula, and it was a great time, and so what he decided to do when he got to Bell Labs was make C++, and it would just have, you know, the classes in it from Simula. It was great. No. So what actually happened was the entire thing completely rolled over and died. He tried to run the Simula program, and he had all sorts of problems with it. And it started even before he tried to run the Simula programs that he was writing. What actually happened is, first, he hit the same things we hit with C++ today. Build times were through the roof, and it was almost impossible to make changes to the program, so much so, and I'm gonna let this sink in for a second because it's really awesome. So much so, I mean, I almost want you to read it. If you compiled 1/30th of the program and tried to link it, it was slower than just recompiling the entire thing. Okay? Let that sink in, because it means that Bjarne was talking about Unity builds in 1994. He was like, we can speed this.
I mean, the linking issues are nothing new. Like, they affect all kinds of projects. And they don't come from objects in any way. They come from number of symbols, variables, functions at the global scope.
Up by not doing incremental. Incremental builds sucked that long ago. Anyway, but I digress. Anyway, the runtime also was lousy. He couldn't get the thing to run fast enough because Simula was extremely slow. Anyone want to guess why it's slow? It's a rhetorical question. They'll tell you why it's slow. It's because of the garbage collector. Same reason things are slow today half the time. The garbage collector was taking 80% of the runtime, apparently, even though there was no actual garbage that needed to be collected, because, you know, I guess at that time garbage collection was even, you know, very, very primitive, obviously, so it's probably running all the time just to see if there was any garbage, and it was like, yeah, nope, no garbage. And that was happening a lot, so 80% of the time. So he had the experience with Simula that we have with C++. Like, it is if the chain continues, right? The garbage collection, obviously not so much. So that's what happened. He had to rewrite the whole thing from scratch in a different language called BCPL, which has no type checking whatsoever. I mean, that's not entirely true. It has very, very minimal, but none of those class things and that sort of thing. So that's the actual story of what happened. So it's kind of interesting. It presages everything, right? The whole thing is almost like a microcosm. So if we reflect on this for a second, again, I think I've tried to highlight the important points there, but the other thing to remember is a lot of people talk about these things. They talk about those compile time hierarchies and all that sort of stuff, and they say, like, you know, here's the thing that you just don't understand. It's all about large teams. You know, it's all about these large teams. It's just that you got to have large teams, and if you had large teams, then you would understand the magic of the compile time hierarchy stuff and the encapsulation. It's amazing, right? How big was the team that Bjarne Strostrup was working with when he figured this stuff out and thought it was good? 1. He's doing the same thing we're doing. So these ideas don't come from some kind of a analysis of what we're going to do with lots of people. So you could argue maybe they turn out to be good for that, but you certainly can't argue that anyone was designing it for that, because they weren't. They were doing it for themselves. Strostrup was doing it for the protection, the type protection, the error checking, that sort of thing. He wasn't doing it to, and also like the virtual function kind of stuff. He wasn't doing it for large teams because everyone at Cambridge University was helping out in the project. No, he was a lone wolf coder. He really was. So anyway, goes to Bell Labs. He makes C with classes, which is the first thing that, it's the original name of C++, called C with classes, because that's what's going to be. It's going to be taking Simula's type system and putting something like that into C. And the reason for that's pretty obvious. He goes to Bell Labs, and C would be like a lingua franca there probably, right? Because they're the people who make Unix, they're the people who make C, like the people who are at Bell Labs, the people making these technologies. So he is tasked, when he gets to Bell Labs, with doing the same sorts of distributed systems analysis that he was trying to do at Cambridge. He's trying to do those things for Unix. He wants to analyze certain behaviors of it and that sort of thing. And he finds like the same exact things. He would like to write in something like Simula. He doesn't want to have the same disaster that he had where he had to rewrite everything BCPL. So he's like, could I take C, add classes to it, and get the best of both worlds? Something that actually runs and doesn't fall over, right? But that has some of these features that I've been enjoying. And so that's what he's doing, and he's doing it for the same reason, right? That sort of modularity and concurrency analysis kind of stuff. He's trying to figure out how these things work and run simulations of them. Same exact thing's happening, and it's happening over again. And what he kind of complains about with C, if you didn't have these things, some of it's a little confusing. Like, he talks about the fact that he says, like, all program parts can poke into all of the memory, and like C++ doesn't really change that. But I think he's just kind of talking about, like, you know, private declarations, right? He's just like, well, you know, obviously I don't think you can stop programs from poking into the memory by putting private on it, but it will stop programmers from typing it into the compiler, and that's sort of the same thing, right? And where that comes from, this sort of idea that we're going to protect things, that actually comes, again, from his distributed systems sort of OS thinking background. Because he's looking at hardware, and he's looking at things like virtual memory and protection that you get between processes and those sorts of things. And he's saying, that's kind of what I want for programming. Like, I don't really want to make those mistakes where I access the private part of things. You know, I want to be able to wall those off. And he's thinking about actual hardware, computer hardware. That's where that idea comes from. Again, it doesn't even come from working on large teams or anything like that. It comes from thinking this might be a nice feature, just like the computer stops it, right, from happening, the compiler could stop it from happening. And that's where const comes from too. It comes from an OS metaphor. He's thinking about whether or not files have write permissions to them, right? Are they read-only or are they writable? That's what const is to him. That's where he thinks about it first. So again, all these things come from a very different place than...
I think constness comes from memory segmentation. So segmentation, it's even present in C, right? A computer, the CPUs which have virtual memory, which support virtual memory, I mean, which is all of the CPUs, pretty much, they have to somehow limit the ability of a program to mess up with memory of other programs, but still allow the operating system to reuse it, to make it possible for multiple programs to read some data without changing it. So a CPU has a built-in mechanism of preventing changes to data in memory, And this mechanism is exposed through const. If you mark a variable as const, it doesn't only change the compile time, the type checking. The point of const is actually to move this variable into a read-only segment of memory. It doesn't always happen, but usually it does. If the variable doesn't have any mutable elements, the compiler can move it into a different segment of the binary where it will actually be protected from being written. So if you cast the constness away and try to write it, the program will crash. It doesn't happen that often. Most of the time you can cast constness away because it only affects global variables, the variables with static lifetime. And constness wasn't new in C++. It wasn't invented by Björn.
What you would think if you didn't go back and read the historical documents. And by the way, these aren't hard to find. Like these just come from the D&E, which is a very popular book that he wrote. That's just a collection of his papers, right? So a lot of this stuff in the first part of the talk, you don't have to dig that hard for. All right. So anyway, we get to sort of a second wrinkle at this point. And what happens when he starts using this stuff is it's important to, I shouldn't really say what starts happening. Let's say one of the things he does is he uses the inheritance that he puts into this sort of C with classes, because he's just going to do the same thing that was happening in Simula. He uses that inheritance in a way that would generally be frowned upon even by him today. And that is to do things like implement a linked list and reuse it. So what he does is he says, okay, I'm going to take a block that's like the linking part of things, and I'm just going to inherit stuff from it so that all the things that inherit from it can go in a list, right? Now, he would never say to do that today. He would say use a template or something like that, like a parameterized type, right? So, but it's important to remember at that time, this was a thought. And this thought actually does come from Simula as well. We'll get to that later. But so it's important to say, in addition to the modeling part, they're using inheritance for the purpose of code reuse, even if it really doesn't have much to do with anything. That's sort of an adjunct split. And I just want to include it here so that you understand all of the things that were being thought about with inheritance at the time when it was actually being put into more mainstream languages. So that's what he was, one of the things he was doing with it, in addition to the domain modeling part, which is more of a direct mapping. Okay, and you can see him here criticizing it just to hammer this home. He doesn't think you should do that anymore, and he said as much in parameterized types for C++, which is where he started to talk about templates. As soon as he sort of got his answer to how we were going to do these sort of things, as soon as he got like a parameterized type model, because that wasn't new to C++, there were languages like Ada and Clue and stuff that had that in there. He started to say, okay, C++ has never had a good way to do this because you had to do the inheritance thing. That's not fabulous. Parameterized types are the way to go. So he knows that too. It just takes a while to get there. Okay. So that's kind of the end of it, and virtual functions come in a little bit later. The first version of C with classes, when he's first starting on it, doesn't actually have virtual functions. He eventually does put virtual functions in, and when he does, this is what he says about it. He says it was borrowed from Simula and presented in a form that was intended to make it simple and efficient. So he was thinking primarily about, I want something kind of like what Simula has for this ability to call functions without knowing the type on them, but I want to make sure it's very fast, because that was a concern that he always had, again, because of the disaster he had experienced directly with Simula. So again, reflecting on this, it's totally different from what you would think if you just read like the capsule summary. Like, he's not talking about large teams still. He's talking about literally, we're just working on this thing. I'm using inheritance for some reuse of code, and I'm using it to directly model the compile time. Yeah, at a compile time, I'm using it to directly model the actual domain that I'm working in, which happens to be distributed systems analysis yet again. So we have to jump at this point, because that's pretty much all we can get out of C++. I mean, you kind of got the picture now. Everything else is like after the fact. Everything else is post hoc. Anything else about C++ was people making stuff up after that, or adding things to it after that. But that's where it comes from. So if we want to actually know where these ideas started from, we've got to go back to Simula. We've got to say, well, okay, if all this stuff came from Simula and him using Simula, well, where did it come from in Simula? Like, did they just make it up? And Simula originally comes from something called the Norwegian Computing Center. I mean,
by the way, Simula's inventor, he did some very nice writing. This is some of my favorite papers on computer science, I've read. Like one of the points of Simula was to simplify programming, right? He was trying to tackle this problem, and yeah, strongly recommend whatever this guy has wrote. I don't remember his name.
Very close to Norway, I suppose. So some of you may have known this place. I didn't really know anything about it until I read that, was reading up on Simula and okay, there's this place. It's a quasi kind of private public institute for doing computing research. And it's in Oslo, Norway. And in 1962, these saucy gentlemen right here, and I'm apologizing, Sweden is the worst place to give this talk because now I have to pronounce their names in front of people who probably know Norwegian pronunciation very well, and so I'm going to butcher it and I apologize. It's Ole Johan Dahl, maybe I can pronounce that correctly, and Kristen Nygaard. And you already know Kristen Nygaard's name because this is the person who Bjarne Strustrup learned the Simula from originally. He was, he interacted with him a lot when he was at his previous university before Cambridge. So these are the folks who make Simula. They're the people who actually are kind of like the masterminds behind it. And the first reference we have to it is in private correspondence that has now been published from Nygaard to another person who was working on operations research. And these folks, operations research, if you don't know what that is, it's when you look at how systems are behaving in order to optimize them, basically. So you can think about things like we're trying to plan how the military is going to organize some things, like what is their process going to be, and we want to maximize the throughput of how we're manufacturing this thing, or how we're going to load planes onto an aircraft carrier. I mean, I don't know anything like that, but a lot of it's military because that's where the funding comes from. But it's for anything really. It's also in business, operations research, things like the simplex algorithm, if you ever heard of that, that's operations research, et cetera, et cetera. So anyway, he says, I got this idea. What I'm going to do is I'm going to make this language that makes it very easy to describe one of these systems. And then what I will do is use it to describe these problems in a way that allows it to do the simulations automatically. So it's almost like a scripting language for system simulation. And if you look, this is some code you can find when they talk about the history of it. This is in 1963, the Simula language would have looked like this. It's one of the earliest snippets I could find. And so this is not the way the final Simula looked. This is sort of how they started out. And you can see what it essentially is, and you don't need to understand exactly what's going on in this for the talk, so I'll spare you the details. But it's actually what you're doing is you're setting up these various things like customers and stations. It's like things, we're imagining like entities moving between parts of a system, and we write little pieces of code that's like how they will be processed when they get there. Like, will this person, they'll be held for a little bit of time, and then we'll check to see if they've paid the fee, and if they've paid the fee, we'll send them to this station. If they haven't paid the fee, we'll send them to this other one. And the idea is you just describe that system this way. You run the simulation, and it presents you with a bunch of statistics. So you can kind of see okay, this is where the bottlenecks were, or things like that, And that was very successful. They eventually released a thing called Simula 1, which was the first sort of more widespread version of this thing. People loved this. They could do their system analysis this way. But Nygaard and Dahl were thinking in their head, we really like this thing, and we think it has possibility to be bigger than what it is. It's going to be more powerful than just what we had in that first version. So they start to make a new version, which eventually goes on to be called Simula 67. And this is it's like Windows 95, right? At this point in time, people are starting to name languages where you append the year of the language after the language. So we have things like Algol having that, or COBOL 60 is the version of COBOL that was first introduced in 1960, right? And so that's what Simula 67 would eventually be. And they're trying to figure out what they're going to do for this new version. And what happens is they're thinking about code reuse. They're like, we don't really like how we have to rewrite things a lot of times, and we're trying to figure out some way that we could get some of this reuse in there. We want to reuse these things, and it's not really working out very well for us. They're looking for a solution to this, and they're not really finding one. But eventually, when they're thinking about this problem, they're saying, what if we have a bridge with a toll booth on it, and we've got cars going across it, and they might be either trucks or buses? What could we do so that we could just write this once and have it work for both the trucks and the buses, so we don't have to duplicate all the stuff we said for trucks and buses? That's what they're thinking of. And this is not me saying this is them saying this is what they were thinking. This is what they were trying to solve. Literally, this is what they were trying to solve when they came up with classes. And here's what those classes look like. You can see up at the top there, it's defining link class car. The link is a thing where they have this linked list sort of superclass that they're deriving from, and they're going to have a car. Then they're going to say underneath cars, they're going to derive a car class truck and a car class bus. There's different kinds. You can see load and capacity are like two different data members that those have, okay? So in this one snippet, we can see both things that not only they are about to do, but that Bjarne Strustrup is about to do as well. We are using this for reuse. We are deriving from a link class to get its functionality, not because we think that we are like a link in the domain model, but then mostly what we're doing is following the domain model with our classes. It is car, and underneath it, it is truck and bus, exactly like would eventually be promulgated as how to design OOPS systems with those hierarchies that I was talking about. So that's what it looked like. And they literally said, hey, this now allows us to quickly just say this thing's a link, and then it can go in lists. Awesome. Now you'll notice they didn't actually talk at this time very much when they were counting the history, and I guess I shouldn't say you'll notice. I noticed because I had to read the whole thing. They don't really talk about the virtual function part at the outset, right? They're kind of talking about just this reuse part. That's mostly what they're concerned about. But they do eventually care about that virtual part, because once they do this subclassing, they're like, we want to have ways that the subclasses can do things in addition to what the parent's doing. And that's where the idea from virtual functions comes from. They say, we have these operations that we were defining, things like what that queuing behavior was going to be that I showed on the original slide from Simula back in 1963. And they're like, we want to have those operations be modified based on whether this car is a truck or a bus and things like that.
I'm not sure where this is going. So this sounds like a
Now, if you look at
history
how
talk.
this had to actually work, it works the same way that primitive code reuse works. If you wanted to use it today, if you want to use inheritance for things like links.
There is one thing in this talk which I totally don't get. From time to time, Casey makes a break, and he makes a statement sounding like he proves some kind of a point. And I just don't get what's the point.
Exactly the same way. They literally had the sort of classes, you can see in the middle there, class SimSet and SimSet class simulation. That's basically saying, like, look, all of this stuff is going to be derived from linked list holder. That's what SimSys would be like. Like, I'm a person who holds linked lists, and then we're going to derive the simulation from the thing that holds linked lists. That way it can use that. So it's almost like a library. Like they're using inheritance like a library here, as well as the domain model, which is under it. So again, that same double duty. All right. So again, just to hammer it home, nothing about teams. Nothing about architecture, none of this stuff, right? It's all about trying to solve a code reuse problem, and then something falls out of that. No analysis is done of any of the things that you would normally say if you were trying to promote the use of domain modeling via those class hierarchies, right? That's not what's happening. So, this is where we actually got compile-time hierarchies of encapsulation that match the domain model. Because Simula actually did have encapsulation. You couldn't refer to things outside of the entities like that very much. And so it kind of did have the beginning of that. It wasn't as rigid as C++, as we'll see, but that's effectively what it was. So I don't know how to summarize all of that we just saw. Basically what I'd say is, effectively, what we sort of were seeing is this came out of sort of an approach to templates that wasn't very good. Like that's sort of what happened. And it's not their fault because, I mean, they're in the wilderness, right? Like nobody knows any of this stuff. We take for granted all the things we know today. They don't know any of this. They have to invent everything. But that's really what they almost wanted. If you had handed them templates at the time that they were trying to do this, they may never have invented this class concept at all because they just wanted a linked list. They just wanted a way to say, I have lists of things going across, right, or whatever. So that's sort of where they had started. And they just happened to come up with a virtual function thing, which, by the way, is useful for stuff. I'm not trying to suggest that it isn't, but that was sort of a byproduct of what they were trying to do, which was just make a list class they could reuse, kind of. All right. So that's the end. That's the entire story. Now you know where everything came from. I mean, of course, if you only want to do sort of the capsule version, that's, again, sort of the Wikipedia version.
I mean, so he skipped the one part which he said he's going to focus on, the part where this idea of modeling the domain as objects came from. he said that it doesn't come from Simula, because he says that Simula was only interested in code reuse. It doesn't come from C++. So where does it come from, right? It's like a missing part.
Of it. But you have to kind of ask the question, I mean, we know that they did those things, but like, where did they get the idea for those things? I mean, that's usually how I approach things anyway, right? I'm like, after I find out that like someone got the idea from someone, I'm like, well, do we know if that guy got the idea from someone? Because I want to know about following it the whole way back, right? So that's the end.
It goes to
if you
ancient
just
times.
Use the capsule Wikipedia summary again, you'd kind of get
To
something
ancient
like
philosophers.
that. What you probably wouldn't get is this stuff. So when you actually go digging in here and you pay attention to every little thing, and every time you come across something that someone mentions, you're like, wait, what? And then you go try to pull the papers that they're actually referencing. You start to find out a lot of other stuff. So if we keep pulling this thread, what we find is the idea of subclassing is not credited to Nygaard and Dahl. They credit it to somebody else. C.A.R. Hoare, actually, the guy who invented quicksort. That's who they say this idea of subclassing came from. They don't claim to have invented it. They claim to have invented a version of it that was derived, pun intended, from Hoare's work, right? And this is the paper that they're referring to. This is the paper that I believe they would have read, although I'm not sure exactly which version they read, because different versions were circulated, and there's actually sort of a further comments one that happens after this, but they would probably be aware of all of this because academics are always very good, right, at sharing their information this way, putting out publications. I mean, it's the thing that is cred for them, right? Like your papers are your cred. So you're reading papers by other people, you're writing your papers. So they read this paper for sure. Which version exactly, I couldn't tell you. But this is the paper, and here's what Hoare is talking about in this paper. He says, all right, we have in the real world, and I want to underline that because it's like compile time hierarchy that matches the domain model, right? In the real world, we have objects that we want to model, and they have different versions of things, and we want to model that sort of discrimination that's happening there in the subclasses. And so he gives the example of an algebraic expression. He's like, if we look at algebraic expression, I'm trying to model that. I want to represent that in the computer. I might say I have an algebraic expression, and then I have these different things that are types of algebraic expressions, right? And he says constants, variables, dyadic expressions, right? He's trying to model language. And by the way, this happens a lot. I don't really cover it much in this talk because it's not relevant, but you'll see a lot of people this time were working on things like how do we parse stuff? Right? So thinking about how do we parse language, how do we parse computer languages, how do we parse human languages, so thinking about this kind of thing all the time. It's like, what if I want to represent an equation? How am I going to do it? Right? And he's saying, what about these subclasses? And he would literally write it just like this. So as we can see, Nygaard and Dahl were not lying. They 100% did get this idea from that. It looks almost exactly like theirs, down to the syntax. You can see that he's saying, I'm going to have an expression. Here are the subclasses of the expression.
Yeah, I actually wonder,
variable, right?
Maybe that's the Casey's point, that he actually wants to end like at ancient philosophers. He's just starting with
what if we just had
old programming languages, and he's going to go there in a moment.
And then we could just use the car, and then we put the car across the bridge. Okay, that would work. Wait, but we don't have to stop at the car. We could make something above the car that's like things that are in a list of stuff. And then we could use it for everything. It doesn't even have to be the bridge. Holy cow, dude. Like, thank you. Thank you, Tony. So anyway, yeah, Anthony, they call him Tony Hoare. I think that was, he didn't go by Anthony. Anyway, sorry, thing I didn't introduce ahead of time. It's just up here because I've been reading this stuff for, I don't know, months at this point. Anyway, so when he presented this in this paper, it doesn't stop there. And this I found so interesting. And we're starting to get into stuff now where like I had never heard before. A lot of this stuff, when I digged into it, I was like, how come everyone doesn't know this? Because it's super cool. When he presented this paper, or I shouldn't say presented this paper, when he wrote this paper, he included discriminated unions in it. Tagged unions, whatever you want to call them, if there's FP people.
This is not quite what he means. So when you look at, for example, when you look at any kind of object in reality, there are often multiple ways of looking at it. If you have a table, right, and within the table there is a cell, you can think that, hey, maybe this cell is part of a column. So like the column is the top level like object and the cell belongs to it. You can look at it from a different side. Like the same object that you are looking at can be described using different objects. We have this capacity to have multiple simultaneous kind of object decompositions of reality. And this is what Hor is talking about. It's not about indicating, I mean, it is because he's saying that he wants to, he can put just a value that will tell him which class it is. But when we think about objects, we can recognize them. We can recognize multiple objects, different kinds of objects in the same entity.
People out there in the audience are going to scream at me for using the wrong term, but you know what I'm talking about, something that has a type in it and then subclasses inside it, and you don't know which one you have until you look at the type, and then you can use whichever part makes sense for that type. And this is a super powerful programming idiom. I use it all the time, and I think it's one of the best programming tools you have for things like dynamic polymorphism. I absolutely love it. It's in this paper in 1966, right? A long, long time ago. And this is his way better than anything I get to use today in C++ thing he suggested for what you would do when you wanted to use one of these. He said it's a switch statement, which of course wouldn't have been called a switch statement at that time, but it's basically a switch statement that says, I want to use this object, and I'm going to tell you what each type, whatever the subtypes might be, I'm going to give you a different block of code to run depending on which one they were.
That would be a nice syntax,
Again, functional programming, I believe, would really like something like this, right? It's doing that discriminated union thing. And furthermore, he gets the fact that this adds type safety and prevents errors. He gets the fact that the code that would come after the then statements can now safely refer to the subtypes because you know you've checked what the type actually was. And he says that right in the paper. So he totally got it. He knew way better than any of the knock-on languages, I guess from C++ on. He knew way better even at that time how cool discriminated unions would be if you had the right language constructs to work with them in a type-safe way. So I thought that was super duper awesome. Now, if you think about it, if this was in the paper, and Simula read the paper, and that's how they created Simula, or the class concept in Simula and the idea of subclass of Simula, and then C++ came out of Simula, well, why don't we have, why wasn't this a first order feature? Where did the discriminated union part go? And the answer is, well, Nygaard and Dahl actually put it in. It was called inspect. So Simula actually had this. You didn't have to use virtual functions. Simula was way better about that. When Strustrup went to do his classes, he took it out. He thought that discriminated unions were bad because they broke modularity, right? It's because now someone from the outside can tell what class you are. So we lost out on one of what I consider would be one of the most important features I would use in C++ every day, because it got removed when Simula was playing telephone with C++. All right, so there you go. That's where the concept actually comes from, right? It's this paper by, Anthony Hor. He's Sir now, by the way. He's been knighted, I believe, right? And again, not a single part of it, there's no hint at all that any of this is really about compile time hierarchy stuff or about large teams or about any of the things we talked about today. It was literally like, hey, I might have a record that wants to have a type field, and it would be cool if I could just switch on the type field and do different things based on it. How about that, right? And that's what I would have wanted. So we had that already back when this paper circulated in 1966. So really the whole string is about us getting a really bad version of discriminated unions. We had them already, and now we don't have them. To this day, I don't even know a standard variant really works as well as this thing would have, right? And we could have had it from day one if someone had just believed that this was good.
So Casey is talking about syntax support for discriminated unions. Of course you can have discriminated unions. You just put an enum or something as the first member of the class. Or you can even use the vtable pointer, like I mentioned. you just look at the first 8 bytes of an abstract class, and this is an address that uniquely identifies your class. You can switch on this.
All right, so that's the actual end. We've gotten back to kind of the point of the first part of the talk. There's another half because it goes way further back than that, but I want to give everyone a chance to kind of stretch out. So I don't know, can we take a break?
So this is my
Where
prediction.
Sam?
We
Can
are
take a
going
break
to
for a few
ancient
minutes?
times.
Yes. How long do you want?
I don't care. I can keep going if you don't want, but I figured, yeah, give it a stretch.
Let's go to 25.
Okay. I'll see everyone back here whenever that is, at 25.
Okay, I'm actually going to use this intermission, and oh no, it was cut out. Okay, so I guess no
Okay.
intermission for us.
So, as you saw in the first part, you come to the end a lot of times, but then it's like, well, you know, is it really the end? If you keep digging, it turns out you didn't really get to the actual meat of, you know, the origin story. You didn't really get to the part where, I don't know, I'm bad with comic books, but like, you know, Bruce Wayne and the falling pearls and the Joker and that kind of stuff. Like, we actually gotten back to that scene, and that's the scene that everyone wants to see in the movie. It's like, how did he become Batman? So what we're gonna do here in the second half, I promise there's only one more half. There's 2 halves, I'm not gonna psych you out again. What we're gonna do here is we're going looking for Batman, right? So we left off, we've got this paper on record handling by Hoare, right? Famous for Quicksort, like I said, one of the fathers of computer science. And the interesting thing is, and this was really hard to figure out, but I was trying to, like, where did he get the idea? Like, did he come up with the idea? Was he sitting around? What was he working on, right? And it's really hard
So
to find
Casey
this. I
has to
wish
know the
that I could
answer to
find
this
a document where he
question.
talks about it. If any of you out there ever find a document, because, you know, I did
He's just
the most research that I could do in
pretending
the
he
time that I
doesn't know.
had to figure out where these things came from, but I'm sure I missed something somewhere. So if anyone can actually figure this out, I would love to see it. But after a lot of digging, I figured out something pretty interesting, which was that actually there was this committee that was supposed to update ALGOL. Now, ALGOL was a programming language that was very popular at the time. It was in use since the early 60s, actually.
Very
Actually,
influential
might have been before
one.
that. I don't remember.
This is
because
the-
it's not that relevant to
A
this
lot of the
particular
C
timeline.
syntax came
But
from
what they
Algo.
were going to do is, much like Simula had an update from Simula 1 to Simula 67, here there's going to be an update of ALGOL up to this new version that would eventually be called ALGOL 68. And the people who were working on this, it's like a who's who of like computer science fame, right? So Hoare is on this, and so are a lot of other people like Nicholas Wirth and that kind of people, like people, the person who invented Pascal or created Pascal, right? So on this committee, there was another guy, and his name was Douglas T. Ross. And this is a name that I had never seen mentioned ever before. I have no idea who this guy is. I'm like, wait, what? And, oops, sorry. And when it was talking about it, it was like, oh, you know, in some private correspondence, because Alan Blackwell and Kerry Rodden, not really a part of the story, but they're like, we talked to Hoare privately about where he got those ideas, and he said that they actually, a lot of them came from this guy named Ross, who he had conversations with when they were on the committee. And I'm like, okay, so what's this about? And Ross had this thing he called a plex, which is a record-like data structure, and apparently this was something that really influenced Hoare's record handling paper, which would eventually go on to, you know, create the rest of the chain that we just went through. So that's one thing. And another thing is, if you look at the other branch, the branch that I'm not really covering very much in this talk, because again, we don't program in Smalltalk these days, right? The closest thing you would get is maybe something like Objective-C. If there's some still people out there using Objective-C, you know, like Apple was using that for a little while. So Objective-C kind of came from a Smalltalk background as well. So, but it's another huge branch of object-oriented programming. Smalltalk was very important. It's influential, at least in the research or in the understanding of OOP, right? It was a very pure OOP language. It pushed OOP a lot further than a lot of the other languages by saying everything is going to be object-oriented and that sort of thing. And of course, it invented the term object-oriented, so everything's going to be like Smalltalk, which is what object-oriented was, right? If you look at what Alan Kay talks about for his inspirations, like where did he get his ideas from Smalltalk? He lists some things, and there's some like the Burroughs B5000 and this file system from an Air Force base that had to do mostly with dispatches. We could go into that in the Q&A if anyone cares. But one of the things he talks about is Simula, which we've already covered, and the other thing is Sketchpad. He talks about Sketchpad all the time. This was a hugely impactful thing for Alan Kay. And Sketchpad was like this drawing program, right? I was aware of Sketchpad. I mean, maybe some of you are aware of Sketchpad. It's pretty famous. You can look up demos of it on YouTube, for example. So we've got this Ross guy that I want to look into more. I'm like, what's going on? And then we've got this Sketchpad thing, and I'm like, I think I remember Sketchpad, but I don't really know why that would have inspired Alan Kay to do object-oriented pricing. So I'm going to look into this more. I want to see, just make sure I've got the whole story before I really say the end like I fake did in part 1. So let's go back even further. 1952 now. There's this place called the Servo Mechanisms Laboratory at MIT, which is kind of an amazing name. I would love to be able to tell people that I worked at a servo mechanisms laboratory, but this fellow right here, that is Douglas Ross, who now I know exactly who he is and what he did. He goes there, and he's first on the job in 1952. He gets to this laboratory. And what their sort of whole mission was, this was Department of Defense, United States Department of Defense research stuff. What they were trying to do is build a system where someone from the Air Force could describe a part that they were going to try to manufacture, and the computer would just make it. It's almost like the birth of 3D printing. And they actually did demos of this. They had stuff working where you could type in a description of an ashtray in this sort of pseudo language that they had that was meant to be kind of more, it's sort of, almost like in a Grace Hopper sense, right? Like something that's sort of, we're trying to get closer to human language, but it's really not human language because they don't have the ability to parse that yet, right? I mean, until large language models, we didn't have the ability to parse that, right? So when you look at something like this, what they're trying to do is say pseudo language, and our automated milling system produces this object out of it, right? And they actually have working, it's not entirely thorough, they've got it working, they have instances of objects you can actually look at that they made. So they're accomplishing this as well, and you have to remember how early this is. 1978 is, I date these by when the person's talking about it. This is the 1950s that they're doing it, right? So they're working on this simulation stuff, this processing stuff, and this where they're trying to take language and turn it into sort of CAD, right? The growth of CAD. And just to show you how early this is in the thinking about what's going on in computing, COBOL is generally again, in the kind of low effort Wikipedia search version, COBOL would be the first thing you'd see referenced as having things like record-like structs, right? We all take a struct for granted. We're a struct is the simplest possible thing, right? It doesn't even have inheritance, or it doesn't have virtual function calls or any of that stuff. We would just say, if we're just talking about a bare struct, a basic vanilla struct, that doesn't really exist. No one's thought about that really. They have sort of an idea of data records that comes more from data processing, in the old IBM sense of the term. So they do have an idea of more of the database version of
So
I've got
in assemblers, some assemblers have macros.
But people
And
aren't
assembler
really
macros
thinking,
were the earliest
when I
structs.
program, the computer program is also going to be written in terms of records that it's using purely for computation.
It's very close to
not
machine code,
store
so
a particular
it's
piece of data,
arguable
on
whether this
magnetic
is
tape or something like this, right?
a programming language feature or not.
Purely an artifact of the implementation of this program, I've defined other records. They're not thinking about that. And even in 1960, when this was printed, this first version of COBOL, even in that 1960 timeframe, this COBOL didn't really have that. All of its record stuff was pretty much still about data on tape kind of things. It was in memory as well when you had a mirror of one, but it wasn't, no one was thinking really about that as far as I could tell. They're just thinking of it as storing data. Now, pedants will say that Plan Calcul has this, but it was a purely theoretical language, just written down on paper. It was an early German programming language. It's very forward-thinking, so I don't want to disparage it at all, but it doesn't count if you just sort of wrote down, well, maybe we'll have this way to put multiple things. It's no matter how rigorously defined on paper, you don't get credit unless you've actually got this working and you're actually programming, making programs in it that you run, right? So really, it's kind of not there at the time. So what people are actually thinking about is this, right? Lisp is gaining some traction here because it's developed over the course of the 1950s as well. It gets published officially in 1960 in this paper by John McCarthy, who obviously was one of the, I believe he's sort of the person who designed Lisp, and actually a different person at MIT actually implemented it, but that has nothing to do with any of this. Point being, he's obviously the father of Lisp because he's the one who had the idea, and he's the one that designed it. And he's starting to talk about Lisp and saying, this is a way that we could do symbolic computation. Now, remember, Lisp doesn't really have any concept of records at this point or anything like that. It's just sequential bags of stuff. So it's like, okay, we're going to have like a list of symbols, and to the extent that you're ever going to do processing on something that's like a record, it's just up to you to kind of remember that the symbols will go in a particular order, and that's how you're doing your processing. So they haven't really gotten this idea yet of structured data, like this is what the computer's going to process. They're thinking in terms of processing lists, right? Because, again, there's like no high-level languages. We got like Fortran coming in this time. We got Lisp coming this time, and then these experimental languages, stuff like that. We don't have all these languages that we know about today. So, Douglas D. Ross, he's also working on stuff like this. They have a programming language that they're working on for this, computer-aided modeling stuff that they're doing, and he's actually thinking, what if we did structured data? Like, what if we were computing on things that actually had a fixed size? And this is all throughout the 1950s, they're developing this. And in 1960, contemporaneous with that Lisp paper, he publishes a paper. And in this paper, he keeps it classy. Right out of the gate, he basically throws shade at Lisp. He's like, look, Lisp is kind of dumb. Why would we compute only on things that basically have a next and previous pointer, or like a tree where it just has a left and a right? What would give you the idea that the things you want to compute on only consist of two things? What you're doing is you're just using that, and then you're constantly building up these like structures of like two-pointer things to represent bigger things. Why don't we just store the bigger things directly? And he knows why. He gets it. He says, look, not only does it take more space, but it also takes more processing power, because we've got to reconstruct the data we actually want by plowing through these lists all the time. And furthermore, we have to store them by keeping all of that interstitial stuff in there. And that's no good either, right? So he is 100% on point, and this is published in 1960, contemporaneous with the Lisp publication, contemporaneous with something like Algol 60. So way, way ahead of the curve here, right? Because that means they had it running throughout the 1950s. Now, he calls this a plex. He doesn't call it a structure. He calls it a plex because I'm guessing he's bad at self-promotion. He never gets this term to stick anywhere, so we don't type plex in front of our thing. But to be completely honest, as far as I can tell from history, we should. It should be called a plex. We should pound define plex to be struct, because that's where the credit actually goes to. It's this guy right here and the other people that were on that team. So what does it look like? This is one of the great things about this era. Everyone publishes everything. It's really nice. And it has to be condensed down into a paper because there's no YouTube, so I don't have to watch hours and hours and hours of things to find out what the heck is going on. This is an example of a complicated plex. This is in the original paper in 1960. And what does it have in it? Well, it has some data, an x and y coordinate, for example, right? It's just things that you might store like you would normally, data members. It also has pointers already, right? These are basically things that are linking it to other things. So we've got data members, we've got linkage members, and hold on to your butts, because what is this stuff down here, right? Like, what is that? And I'm loving this, by the way, when I find this stuff in papers, right? Because I don't like to just read the abstract. I want to read the whole paper. Like, I paid my money, and I want to see the whole movie to the end. Even with the end credits, even if the movie sucks, I kind of want to know. I'm just curious right now. So I'm looking at this, I'm like, what the heck is that? TRA 562? Like, some secret code stuff going on. So what these actually are, and this is awesome, is check and fast are basically flags. And what Ross says is, look, when we're processing this stuff, think of it this way. We could run one subroutine, and just based on what we stick in the plex, we could change how we're processing it. So if we do want this thing to go through a particular path, we set it, and if we don't want it to go through a particular path, we don't set it, right?
This sounds like some
Just pause for effect on
overinterpretation.
that one.
It's like a Boolean, right?
TRA 562, what's TRA 467? Those are addresses, that's an instruction. It's saying what we're going to do there is jump to a subroutine. Those are function pointers. So he basically says sometimes we don't really want parameterization of what's going to happen. We just want a completely different thing to happen. And there is where you basically have your virtual function staring you right in the face, right there in 1960, contemporaneous with Lisp. So I'll just say, our team, yeah.
This is a very bad way of looking at this. Like saying our team, their team, it's like trying to manufacture conflict. It's good for clicks, but this is not how programming works. Like, programmers are not divided into any teams.
Ryan, Team Fat Strut, we started in 1960, right here. We're like the old sort of thing at a university, like the old sort of club, right? That's going forever. We got roots, man. We got roots. We got hardcore stuff on our side. All right. So he throws up an example. He's like, hey, let's suppose we want to model a line, because remember, he's working on CAD. He wants to be able to type in, this is the shape of the airplane engine, and out comes the engine. So we're trying to think about things, how do we model lines, how do we model surfaces, that sort of thing. He's like, well, one thing we could do is we could take the data for the line, and we could put it in there. So those are like names of things, and X and Y coordinates things for like points. And then we could have like connected up with pointers, so a line would have a pointer to two different points, and the points would point back to the line, and we'd make basically a winged edge data structure, right? I mean, these guys were off the charts with what they were doing. It's kind of crazy, but doesn't stop there. So that is at the Servo Mechanisms Lab, which later gets renamed to like Electrical Systems or something. It's a lab that's still around today, I believe, but it has a slightly different name. I think it might have said it was even one of the longest running labs. Anyway, so hardcore, but there's another MIT, it's sort of like out, just not on the main campus in Cambridge. It's off in Lexington. It's called the Lincoln Laboratory, also very prominent. And this is the other side of our story. Remember I said we have this thing where CAR Horace saying, I got these ideas from Ross. He was pretty cool. And then we also have that Alan Kay part where he's talking about, hey, Sketchpad. So we haven't talked about the Sketchpad. We found out about Ross, and he was hardcore. What about Sketchpad? How hardcore is that? Well, this is Ivan Sutherland. He's the guy who made Sketchpad, largely by himself. Like he pretty much wrote it, again, lone wolf style. And he comes to the Lincoln Laboratory in the summer of 1960 as an intern originally. But he ends up doing his PhD at MIT here. So this is what he's doing. And in the course, there's these computers called the TX series. There's like TX0 and TX2. And they're basically made by this guy named Wes Clark. This is at MIT, and they're making the computers, right? I mean, that's the way this stuff worked back then, is like the university actually had to make computers that they would use because nobody knows like what a computer even is yet, and they're like building different versions of them and figuring out what the heck's going on. And this TX series of computers, they were pretty unusual because they actually had a display. Like, we're back in the 1950s, right? So the idea that a computer was going to draw a picture for you that wasn't on a plotter that would like draw on a piece of paper is like completely unheard of. Like no one's doing anything like that. It's very rare. And so there's only a few places in the world that even have a computer that can display something. But the TX series of computers can. And this guy who was architecting them, that Wes Clark guy, he was very forward thinking as well. And he was basically saying, I think there's something here. I'm going to make it so it can integrate with a light pen that can like see what's on the CRT, and I'm gonna like have the CRT be able to display stuff that the computer has. So he makes this new computer called the TX2, which is an iteration of TX0. There's no TX1, I'm told. I don't know the story behind that. But he makes a thing called the TX2, and obviously when you make something like this, it's hard to get time on it because it's just there's this one that was built. But he makes this, and it's under a thing for the Air Force, the US Air Force, where they don't really care what you do with this computer. They were funding it not because they wanted MIT to compute something for them, but because they wanted MIT to figure out what happened with large arrays of transistors for computing. Like if we make big computers, what happens? So this is very helpful because it means that the computing time on the computer isn't necessarily being taken up by some specific grant thing that they have to do. It's more flexible. So Ivan Sutherland manages to convince Wes Clark that he's got this idea for being able to draw on the surface of the thing, make like a drawing program. Could he have a slot on the TX2? And thank God Wes Clark said yes. Because from then on, Sutherland went in at 4 in the morning, because that was the slot that was open, to work on this thing. That's the TX2, and that right there is actually Sketchpad running. And so he would work on this, and I mean, when I say work on this, you'll notice it's not like a keyboard here. You're not like typing in code into an editor. It was still like had to be manually entered in various ways, right? There was actually like a secretary who would enter some of it. He entered some of it, right? So it's very laborious to develop things in the 1950s. Again, just to kind of hammer that home, these guys did not have much to work with. But he's working on this Sketchpad program, and what you could do with it is stuff that we completely take for granted today, as stuff you could just do. You could do things like draw lines with the light pen, just like we would with a mouse. And it's actually fairly intelligent. It knows things like snapping, like if you go and you're going to connect back to a point, it knows that. It's not stupid, right? So it's not just doing random line drawing, it's thinking about those lines as well. We'll talk a little bit more about that because there's a lot more to cover there. But Alan Kay, who I said was the person who got us into this in the first place, the reason we're looking into it, he calls Sketchpad, the eventual thesis that Ivan Sutherland would publish on it, he calls it the most significant single thesis ever done. He says that it was like so impactful and so important, not just to him, but to everybody. And honestly, he's probably right. Out of Sketchpad comes a lot of research in computer graphics. It comes the whole object-oriented concept from Alan Kay. The whole idea of interacting with a computer in this way is very, very new. CAD, and the idea of a CAD program kind of comes out of this as well. Now, it's so early in computing, I just want to hammer home one more time the kinds of things that Sutherland talks about if you read about his experience with Sketchpad developing at the time when he published the thesis. No one's ever even thought about, like, if I want to draw a line and then change where it is, I don't have to erase the line anymore. I could just move where it is. This is a completely new concept that no one's ever thought about before, because for the rest of history, if you drew a line, you had to at least remove that line before you drew it again, right? So they're literally figuring out here in real time the kinds of paradigms that we just take completely for granted when you sit down to use a computer. The fact that you can move things around by pointing at them, completely new. That's what we're talking about here. Another example of that is rubber banding. They were thinking, oh, when you draw a line, you must have to move the light pen along the line to draw the line, just like you would with a T-square or something like that, right? And they were like, wait a minute. We could just have the light pen attach the end of the line and move it around until you got it where you want it, and then you could let go, and that would be where it was. So even basic stuff like this was news to them. They were discovering it, right? So it's really, really early. That's how early we're talking about. Now, as fate would have it, when he's working on this program, who walks in but Mr. Douglas Ross? They were at separate laboratories, but they did talk to each other a lot. And the reason for that was because Ross's group is working on CAD. They're not displaying much about it, right? They're not working it interactively, but they're trying to do these like machined creations that are based on human input. So because Sutherland's pretty new to this stuff, he talks to Ross and he's like, how do I make stuff like lines? Like, how do I do that kind of data modeling in the computer? Do you guys have ideas? And Douglas Ross is like, have I got an idea for you? It's called a Plex, right? And as we saw, Plex is pretty awesome. And Ivan Sutherland is probably one of the smartest people on planet Earth. So he recognizes right away this is a good idea too. So he's like, all right, we're doing it, right? He says, what I'm going to be making this program to do is have a bunch of like primitives, right? Like I've got lines and things like that I'm going to create. And I don't have that many types of things. Like I'm just going to have like lines, and later, actually, it was Claude Shannon, the father of information theory, right, who says you should put circles in it too. So there's all this kind of like.
Speaking of influential papers, I would say probably Shannon's paper. Probably, definitely. Shannon wrote a paper called Information Theory, which introduces basically half of the math that underlies communication, like information content. He essentially formalized the idea of information and noise.
Little answer. If you actually go read this yourself, you'll find there's so many things I couldn't fit in this lecture because it would have been like 8 hours, right? But anyway, so he's saying we're going to have all these instances of things, lots of lines and stuff like that. So I don't really need anything more than just this end component thing, and I'll just have lots of those, and that's how we'll do it. This is how I'm going to write the program. And here's his diagram from his thesis about how he's going to structure, right, how he did structure lines and points, right? And there's some information missing from this because, if you're sketching things in Sketchpad with that light pen and it's very slow, right? He can't make slides with software like we have today. Not that the software I used to make the slides was particularly better than Sketchpad, but you get the idea. So it's not completely documented in here, but you can see here it's got the line, it's got a pointer to each of the points and so on, and the coordinates, so he's sort of sketching that out. And hey, it's exactly like that paper from Doug Ross, right? And Doug Ross published this in 1960, so Ross and his team were already thinking along these lines before Sutherland even got to the lab, right? And started working on Sketchpad in the a little bit later in the early 60s. So that's how this whole thing ties together. Ross and Sutherland are like having a huge party here, and it's awesome. And if you remember, we had these things in the Plex that were basically like jumps, right? They were like subroutines. They were the virtual functions at the time, or we maybe would call them not necessarily virtual functions, although you could implement that way. We just called them function pointers, right? And you can do all the same things you can do with a function pointer. That was something that Doug Ross was talking about in his Plexes in the original paper, and it's right there in Sketchpad as well. This is how he did things like, I want to go ahead and draw this shape, but I don't want to bother having actual different data types be completely specialized, having the routines completely specialized. So what I'll do is I'll just have like a few entries in the data type that say, how will I display it? What would I jump to display it, to figure out how big it was, or to move it. So again, virtual functions, right there, they come from the Plexes, he puts it in, and that is how he actually implemented that kind of like parametric behavior in this program, in Sketchpad. Now, because we've already got one applause line before for this kind of thing, I'll just point out there's empty space in between these things here. And on the previous one, I was like, well, the reason that there's empty space on those is because we probably didn't have time to draw it out, and that was true for that diagram, because I know more about the data structure because I've spent way too much time looking at this program. But in this one, those are actually space in the struct. Those fields there's gaps, right? So why are there gaps? Why were there gaps in this thing? And I wanted to know, so I'm coming through this, just like, what are the gaps about, right? Is it just the same as the other one where it was like you just didn't draw it in there or something? What are the gaps about? I found it. At present, all generic blocks still carry space for all the information in any of them simply because of historical reasons. This accounts for the spaces seen in figure 3.7. What this means is Sketchpad is on Team Fat Struct, right? In 1963.
This Team Fat Struct, this is really toxic way of talking about programming. This is really unhealthy.
He was still doing the same thing that the Plex was doing. He was just saying, look, maybe I should have gone back and tried to figure out some way to compact these, but you know what? We didn't end up doing that. And so he kind of just has that mention there. It's like, yep, all of them are the same size, and we just leave those fields out if they weren't going to be there, right? So I'm bending it a little bit there because in the Sketchpad paper, it's very hard to tell exactly the way, because he doesn't give explicit data layouts for a lot of things. It's hard to tell whether or not he was using like things that always had fat struct, or whether it was more like semi-distributed unions, so there were pairs of things that would have been used differently. So it's either team fat struct or team overlay fat struct, but it's one of the other. All right, so we've come to the part where we can build our tree. As far as I can tell, it doesn't go any deeper than this. This is where it actually started for reals this time. Doug Ross and his team this idea of plexes. It goes to Ivan Sutherland because he works there, and he asks us for their advice on how to build the stuff in Sketchpad, and he picks up the Plex concept. It also goes to CAR Horror. That Plex concept goes to him because they sit on the Algol committee together. So that's our first branch. We then have that horror paper was read by Dahl and Nygaard, who decide to use it to create their Simula class idea. And both of those, the Simula and Sketchpad, influence Alan Kay to create the Smalltalk branch of OOP. Meanwhile, the experience with Simula influences Bjorn Strustrup to create C with classes and then C++. Now, by the way, this is an inheritance hierarchy that matches the domain model. But there's a fun part.
I saw this coming. It was obvious when he started drawing arrows.
Some of you may not, because, I mean, why would you? Obviously, we know C++ has multiple inheritance. It got multiple inheritance, not right away, but it got it eventually. Smalltalk never did. Single inheritance. However, single inheritance will get you C++. But it won't get you Smalltalk. You need two parents, right? What can I say? So that's the actual end. Now we've built our tree. We're finally done. We know where this stuff came from. Whew, right? It was long. Of course, there is a personal angle to this as well, so I should probably say that the reason I decided to go do all this, it probably wouldn't be, I'm on that thing called the internet all the time. And most of the time, I'm just going to post something snide as a reply and not think about it again. So why did I actually go and do all this research just for this? Why didn't I just say, who cares about these things? I don't use those compile time hierarchies and just post something mean on Twitter. Why didn't I do that this time? It would have saved me a lot of time. Of course, I wouldn't have had anything to present today, but it would have saved me a lot of time. Well, here's why. Back in 1997, which by the way is right around the same time that we started this talk, right? The Looking Glass stuff that they did with entity component systems was 1998, which means they would have been working on it in 1997. It would have been up and running at that time, so it's right at the same time. I'm with a fellow called Chris Hecker, and I'm brand new. Like I'm literally out of high school, so I don't know anything. Like I programmed a ton as a kid. But if you ask me, my thoughts on computer architecture or something like that, I obviously would have answered very confidently and been completely wrong about everything. So he says, we're going to need a level editor. This is basically a game that we're working on. We need a level editor that does CSG on spheres. So the idea was you'd take these spheres and you'd build the level up out of unioning them together, right? Like a standard CSG modeling kind of stuff. But of course, I don't really know any CSG stuff. I really know how to do that. So I go using, I think it was Sightseer at the time. Like nowadays you might use like Google Scholar or something to search for papers. So I go to use like Sightseer, I think was up at the time, or maybe there was a precursor to it, and I can't remember the actual one, but there were things at the time, even then this early, because the internet's, the internet's only been available to the public for a short time really, like it was ARPANET, until the mid 90s, right? So when we're looking at this, I go to crawl papers and I'm like, okay, CSG on spheres, like to try type some things, some papers, what am I gonna do? And I come across this thing called alpha shapes. And alpha shapes are just the name that someone in a paper had given to something that was basically implicit services. I don't really know why they called it alpha shapes because it escapes me now. I'm sure I knew at the time because I had just read the paper, but for some reason they were talking about these alpha shapes. And I looked at them and was like, oh, it's like spheres, but when you move them together, they make this like nice smooth join. They don't make that hard edge. And I was thinking, oh, for levels, that would be like really cool. That might be like way better than if we did CSG on spheres because it would have this like really cool effect. So it was kind of be like on the inside of these things, which are typically called metaballs, and it was going to be like sort of the negative space of the metaballs. So I made a modeler for this, and I called it Negaman, which has nothing to do with Mega Man, completely legally distinct from that. It's kind of change one letter, and maybe it's the same, but nothing to do with this. It's just negative space metaballs. And this is what it looked like. And effectively what you did is you picked things in it. You can see those spheres there. Metaballs. They're the kind of spheres you put together, and they form these kind of surfaces. And we're seeing the inside of what you're creating, right? Because it's a negative space. So that's why it looks kind of weird. You would normally see the outside in a metaball modeler. Well, this is what I was working on. Well, I mean, and it's finished. Like, you can use it. I still have it to this day. You can.
Oh yeah, I have this issue that when a debugger attaches to one of my programs and it crashes, sound stops. CD call stack. What is wrong? What is wrong? Distractor for segment tree. Distractor for segment tree. Fascinating. Am I mixing the values? Locating t, subtracting 1. So before I delete, I have to add 1 back. Makes sense, right?
And so the way that you interacted with it is you like picked those spheres and you could move them around by dragging the mouse and that sort of stuff. The same sort of things, right, that like Sketchpad was doing, only, you know, with much better hardware and much more advantages in terms of development. Same kind of idea because, you know, like Sutherland was so far ahead, right? And so if you wanted to create stuff, you might select things like here. I don't know if you can see it. I've selected those 2 metaballs at the top, and then I've just like, there's a thing you could like rapidly stamp them down. I kind of just drag them and like stamp, 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 and you can create more of the level, just kind of like blobbing things together. So it was a selection-based UI, like most programs are, where I select a bunch of things, and then I wanted the program to basically have a nice architecture for being able to do that, and then present the user with the user interface that would be appropriate for that selection. And this is actually a really hard architecture problem if you're not experienced, which I wasn't. Because it's like, well, if what you've been told is that you make these hierarchies, like these class hierarchies and things like that, and what we're really saying is, I'm going to select all these things that are really derived types of things, but now I want this higher level thinking thing to look across everything that you've selected and come up with a plan for what the unified interaction would be across those things. And then when you actually want to do the interaction, it's got to make sense for what's going on. And this is really tricky because the inheritance hierarchy thing doesn't help you at all for this. It fights you. You're constantly like, oh, do I just add a bunch of like functions to the base class that's anything you might want to do to a class? Do you basically fatty struct your interface, right, but leave the hierarchy in place? There's all these things you might think to do, and they just don't work very well. But I was, you know, pretty gung-ho at the time. You know, I'm not old like I am now. So at the time, I don't mind typing a lot. So I go to town on this. I'm like, all right, I'm going to try to figure out how to do this cleanly, quote unquote, and we end up with crap like this. Now, a lot of times I try to convince people. I'm like, look, everyone thinks that I was like some C-only programmer. I just don't know anything about like huge, crazy, hairy, object-oriented programming or anything like that. It's just like, you don't understand. It's like, no, dude, I wrote some of the most ridiculous OOP stuff you have ever seen when I was like 20. I was doing crap like this all the time. It was awful. I'm not proud of it, but here is what's going on, right? So the way I chose to solve this problem, never mind the fact that like I'm doing the implementation inheritance thing up there with a template on the class. If you've ever seen this trick, it's an old school. So it's like there's so much stuff in this code base. It's a nightmare. But anyway, so if you look at what's going on here, I have get and set functions like you're supposed to
So this
have
is CRTP. This is fairly
on
standard.
any proper object. And you can get the center, you can set the center, that sort of thing, get the service radius, set the service radius, right? And now what I want to do is I want to have some way that these can be interacted with in a unified way. So what do? Anytime you create one of these things, I build a parallel structure. I create a property list that basically is callbacks using, this is called a rich Hickey functor. I'm not kidding. It was a callback that you could use to do type-safe callbacks back in the early days of C++. I'm trying to tell you, where's the camera? Seriously, like I have done ridiculous OOP stuff. But if you don't believe me after seeing this, I do not know what to tell you. We can post more of this code if we need to. So anyway, so basically when it's created, it creates a parallel hierarchy that's just, it's not actually the properties, it's just callbacks that would get and set the properties, right? And then, you know, this is what that class looked like, right? Here's the get and set callbacks abstracted into a property. And then, if you wanted to use it, you could loop over the properties you could create a modification that was typed on the property, right, to do the changes you actually wanted to do. Okay, and that's to support like dragging and undo and things like that. So this is what it looked like if you drew it out. I have a metaball with a radius and center. The data's in the metaball, right? Just like a good object-oriented programming thing would tell you to do. It's encapsulated inside the metaball. I create parallel, I call them property universes. I create property universes, all of the center properties, all of the radius properties, and they are callbacks to modify or retrieve the data in the actual entity here, right, the metaball. And then when you interact with it, you use modifications to interact. And this way, when I wrote the code, I could think about things in terms of the center or in terms of the radius. So what I do is when you multi-selected, I'd go, what are all the property types that you've had? And I'll just make interactions that work with those property types. And I'll put up little UI elements that work with those property types. If the diagram looks familiar to you, it's because you had memory, because this talk is very long. If I had a brain, I would have realized you don't need that. Just put the properties in the actual universes themselves and use an ID for lookup, and it's an entity component system. It's the same architecture, it's just I sucked at it and Looking Glass was good. That's the difference, right? So anyway, this was a slide I showed at the beginning. This is the slide that I did. You see what I'm talking about, right? My bad, right? This was my bad. I screwed up. I say that I don't blame myself because I was a kid, but really, I mean, I should have thought it through. So anyway, in 2024, when I was accidentally on the internet like I should not have been, I'm thinking to myself, how the heck did Sketchpad do this anyway? Because they must have had like the same problems that I had, because he could do all this stuff. It wasn't just a shape drawing program. I withheld some information from you if you've never seen Sketchpad before. I apologize, it's for dramatic effect, it's worth it, trust me. It could do a lot of other stuff than just draw. The just drawing stuff is the stuff that like Adobe copied or things like that, because that was the part that they could understand. The hardcore stuff, only Sutherland knows how to do. And here's what that looks like. You could say I want these lines to be like perpendicular to each other, and it would do it, right? You could take a drawing like this and pick a point that's not even a point, it's the intersection of two lines, and not just snap, but say, I want this radius from now on to always have its center point, like the circle arc, it's going to be drawn around that intersection. And not for snapping, but for always. So that if I then go do some constraints on this thing, which Sutherland's about to do,
This
he's going to say,
is
make
constraints,
that
like he said it. This is how you do it.
that, perpendicular to that.
A constraint is just a
Which
function
you can't do in
that,
anything from Adobe, right? You have to
that continuously adjusts the values based on some like input values. Typically, if you have multiple constraints arranged in a like series, it leads to kind of unstable, wobbly simulations. Sometimes you can use constraint solvers to do this consistently, but they are very rare thing. Like in complex problems, you very rarely get to use constraint solvers.
go get AutoCAD or something for this. And by the way, AutoCAD didn't add it till like 2007 or something like this. They didn't have it in AutoCAD for like, right? When you tell it those things, you say, okay, that's what I want my shape to be, it'll just solve it for you. And if you move it, move the points around, it'll solve it again into whatever the closest shape is, right? Using like a relaxation least squares kind of thing. And I'm like, what the heck? I remember this, because I'd seen this demo before, and I'm sitting there thinking, you know, that whole compile time hierarchy thing in Alan Case, like he saw Sketchpad, and so I'd known those parts, you know, all the details I had to learn for this talk, but like,
Okay,
what the heck did he do? He's working on this like crap computer. I get that he's way smarter than me, so fair enough, but he still had to do something, right? So what did he do? what does a really smart person do when they're faced with this situation? Because he's creating stuff that people who came after him, who have like crazy debuggers and WYSIWYG editing and the ability to run things quickly and iterate, they don't have to go in at 4 in the morning and enter things manually into a computer. How did he do it? Because no one did it afterwards for decades. So let's take a look. If we go in and we look at how he represented constraints, he represented constraints by saying there's going to be variables that are constrained. So I'm going to have some variables, things like this point or this line, that sort of thing, would be considered a variable in the system, something that is like a very primitive element of the system. So it could do that. You'd pick those, and then you would have a certain type of the constraint, essentially, which is like, what am I actually going to be doing with this particular constraint? But they're relatively generic in this way. And then the things you could constrain, scalars, points, instances, text, digits, and dummies. These are the different things you could constrain. They're sort of all like, again, sort of almost team fat struct there, right? They're kind of like all things you can reference as a variable without needing to know which one you're looking at. And so you can remember when we were talking about here's how those lines and points are, the line would not necessarily be something that was constrained, right? Because it's kind of it's a bigger thing than those are. But the points would potentially be something that was constrained, right? So you might say things about them in that way. And I don't know all the specifics of how the constraints work because he doesn't publish, like in the thesis, it only talks about it to a limited degree. So I can't give you a perfect breakdown of exactly every piece of the system, but I mined as much out of it as I could. And he goes on to talk about how this thing was architected so to solve things. He said, the ring structure, which we have not looked at yet, was designed to permit rapid constraint satisfaction. So what is this ring structure? What does he mean by that? But he's pinning it on that. He's like saying the ring structure was really important, and that's what let us do this. He also says, all references made to a particular component element or block are collected together by a string of pointers which are written to that block, which is kind of a type of ring structure, right? And he says this, which really throws you for a loop at first reading this thesis, in the data storage structure, the separation of general and specific is accomplished by collecting all things of one type together as chickens, which belong to a generic hen. Now, I will save you the trouble, those of you who want to read this thesis about what those mean. A hen is a sentinel of a linked list. A chicken is a link in a linked list that points back to the sentinel, essentially, right? So here is how the data is laid out. Type is a chicken, link, quote unquote. Spec B is a hen. So now when we go back to this type that we've already looked at, we can see them up there at the top. Type is the chicken, spec B is the hen. This is sort of the workhorse of the structural elements of the system. And the way that it works is that chicken at the top links it into a giant linked list with all of its siblings at its level of whatever it's doing. And the spec B hen is the sentinel for the list of all the things that are like subordinate to this thing. So it's like an up and down kind of a thing that's going on there, right? So chicken and hen. Here is how he actually draws it. You can see it's just a linked list, exactly like we would expect. Key or hen threw me for a long time until I got it. Key or hen just means hen. For some reason, in the paper, he never says what a key is until this one part where he's like, sometimes I also call a hen a key. So anyway, okay. He then goes on to present this. And this is the runtime structure of Sketchpad. You start with a universe, and it has a sentinel, or hen, right? It has a sentinel that has a ring inside of which is variables, holders, constraints, and topos. Again, not a compile time hierarchy, actually a runtime set of rings, right? So this is not baked into the compilation of this program in any particular way. It's just how the rings are structured at runtime when they are built. There are variables, holders, constraints, and topos. The ones we care about in this case, we don't really care about the holders much for understanding, but the topos are lines, circles, and pictures. Pictures are just like copies of things, like copies of other drawings, right? So the topos are the things that we're actually sort of the users interacting with. At a higher level, the variables sometimes, like they see points and things like that, or text things they can edit. The topos are made up of those variables, right? A line is made up of points. And then the constraints are things that you apply to them. Now, it's important to notice, this is sort of, you could say, the opposite of encapsulation. What this structure implies is that at any time, any part of the system can go looking at anything. It's almost like a complete introspection system for what's going on.
Yep.
A topo, for example,
It's amazing.
that is a line, is not
This is how
encapsulated at all.
I believe programs should be
The 2 points that
written.
make it up
Like even
are just
object-oriented,
floating in the breeze
they
over
just should
there
have
that you
access
can
to other
go just
objects.
grab, right? And you can do whatever you want to those points without that thing even knowing that it happened, right? So it's almost like the most unencapsulated thing that you could possibly imagine, which is probably why it was so cool. But if we draw it, oops, well, it kind of looks like this, right? The topos, you have a circle, it's got a radius and a center. It has pointers out to those actual things, which we call variables. Those are the scalars, those are the points. And if we have something like constraints that's going to operate on them, it just points into those things. And all of these pointers are typically like bidirectional. Like that ring structure is allowing you to walk in both directions if you want to, right? But this is the way that you're actually like conceptualizing the link in those cases. Once again, the same diagram, more or less, than what I had to write, which is the same diagram, more or less, than an entity component system is, because you are able to iterate over all of the properties you want to work with, which lets you implement things like a constraint, or in my case, a modification, right? In this generic way that operates on the pieces of things, or components in entity component system language, in a way that doesn't require this sort of weird abstraction thought where you're trying to figure out how to get things out of something in order to work on them. That was in 1963. So, to a first approximation, Ivan Sutherland was at the same level of closeness to an entity component system in 1963 as I was in 1997. And then people didn't notice? That's the only thing I can figure out. I have not found anything except for one quote that I'll show you that explains why the heck no one realized how important this was. They didn't think about the fact that the power of this system is coming from the fact that you can look at these components of things and architect around that instead of architecting around the bag, which who cares? Again, still object-oriented in its thinking. You don't have to claim it's not OOP. It can still be OOP. It's just where are the those encapsulation boundaries? Where are the boundaries, right? Instead of looking at it and going, oh, the important place to put the boundary was around this, that's where the power is coming from, they're looking over here. They're like, the power of this system was that. The ability to have virtual functions on it, right? The ability to say, if I want to draw this a different way, I change the subroutine. Now, I'm not trying to say that isn't useful. Function pointers are good in certain circumstances. But what inevitably happens is they're only going to get you the simple stuff. The only reason that even worked for Sutherland in the display case is because his display was simple. He didn't have to do things like intersecting stuff for hidden line removal or doing some kind of calling on it or who knows what. So he could just have an abstract display function because it never interacted with any other part of the system. It's the least interesting part of this architecture. Yes, it's cool. It's Doug T. Ross's idea about plexes. It's where it comes from, right? And that was a great idea, and we should keep it, but it's not the cool part of Sketchpad at all, right? It's the most trivial part of it. So that is the 35-year mistake. Oops, right? We had the answer. We could have been so far ahead if we just studied that and figured that out. Because it's so much more powerful to think about systems that way, especially the hardest kinds of systems like editors. This is the quote I was talking about. So, you can see here, this is Alan Kay, father of Smalltalk. And this quote breaks my heart, because I like Alan Kay. I think everyone likes Alan Kay. Probably, I don't know, maybe not. There's probably someone out there who hates Alan Kay. But Alan Kay is very forth. He was trying all kinds of cool things. Xerox PARC is awesome. I'm not going to say something negative about Alan Kay. I'm just not going to do it. This quote breaks my heart because what he says in this quote is basically that the constraint solver, which he obviously knew about, because I happen to know that Alan Kay read the thesis. That's documented. Alan Kay says he read the thesis. And he paid attention to the constraint solver part. And he paid attention to it enough to know that what he called it omniscient. He was calling it omniscient, right? This idea that it could look at the properties like that and work on them, and Kay thinks it's a bad thing, right? He says, hey, there's this thing called Alan Boring's Thing Lab, which is another program that was made later, a first attempt to go beyond Sketchpad, and he devised a nice approach for dealing with constraints that didn't require the solver to be omniscient. The omniscient part was the good part, right? That was the thing that was so powerful. It's why it's kind of torturous to make things in small talk. I have dabbled in it a little bit. It's like, no, the encapsulation needs to be in the right place. You don't want to think of everything as these small little objects. So why did they? Why was Alan Kay so focused on that stuff? Why was Strostrup so focused on that stuff? And honestly, from reading it, oops, didn't mean to advance there or to go back there. From reading it, this is my best guess. Their backgrounds predisposed them not to want this, right? You look at where they come from. Strostrup comes from distributed systems. Alan Kay had a degree in molecular biology. They're both thinking of little tiny cells.
Yes, if you listen to any Alan Kay presentation, he keeps bringing this analogy of programs to cells. It's a very bad analogy. We don't want programs to resemble cells. Cells are just ridiculously complex, and they have a lot of mechanisms that are meant to ensure that the cell will survive, like redundancy and a lot of barriers. Within cell, you have tons of just barriers, like the outer cell or the core. The organelles within cell, they have their own barriers around them. And it's not necessarily the best analogy because we do not have any sort of cell engineering theory. I mean, maybe there is some, but cells are generally evolved systems that kind of work because they kind of evolved those behaviors. They are not engineered. They are not created to be easily understood. They are created to survive in a hostile environment. If we design programs like that, they are going to have the same properties. They will be good at surviving in hostile environments, but not necessarily be very good at being modified by some designer. Distributed systems sounds like a better background for designing computers.
That communicate back and forth, but which do not reach across into each other's domain to do different things. And so they're certain, Alan Kay especially, that is the future of how we will engineer things. They're going to be like microorganisms, where they're little things that we instance, right? And they just talk to each other. So everything will be built that way from the ground up. But the problem with that is it doesn't seem to work in practice. It's a great idea when thinking about systems that are actually separated in that way, like actual computers talking over a network. It makes perfect sense because they do look like microorganisms. And most of Alan Kay's ideas actually map very well to things like the internet writ large, where you really do have to just pass messages back and forth. So again, not going to say something negative about Alan Kay. The ideas are good, and they do have very good applications. It's smart. It really is. But when you're talking about code that's working inside one computer in the same core memory that's meant to work together, it's too limiting. It's way too limiting. It's not the right model, and it forces us to do way too much work to accomplish the same thing. So, just to underscore, reading this history actually gave me a nice perspective on these things. And I think there's reasons why C++ was adopted, even after all the stuff I just said about how the compile time hard stuff wasn't very good. One of the things that I didn't really appreciate was it kind of sounds to me like Shrustrup was really important in getting type checking for us. Like C did not even type check function calls at the time that Shrustrup was making C with classes, right? And he recognized, because of his background in Simula, he's like, this is ridiculous. I think he gave an example like, if I do square root, like sqrt in C, parentheses 2, that doesn't work right now because it passes the integer 2 and it doesn't check that square root's taken a double or something, right? Or whatever it was taking in that particular version of the library he was using. He's like, that cannot be something that we have to catch at runtime, especially not in those days when debuggers are worse and everything is worse, right? Iteration time is slower. So you get this situation where you're like, I kind of see why these things took off. Some of these things, like the compile time, encapsulation hierarchies, they're coming in at the same time that C++ is making positive contributions that actually do help you program for real, right? And it's not like we can't think of uses for things like virtual function classes, like interfaces. Just that bare concept is a place where we still use those things today, even in new languages. Used responsively, right? It's just that compile time hierarchy that was a problem. And this is a quote that I also want to include just to give Shrustrup credit. He's also on the same team. He wants the fast thing, right, to be easy for people to do. You don't want your definition of good code to be slow, right? So anyway, when you read through all this stuff, you're kind of rooting for everybody. To be completely honest, even after all the suffering that C++ has caused me in my life, I was kind of like, oh, all right, I get it. I get it, man, I do. So that's the 35-year mistake. It's the distance between those 2 years. The year in which we could have had the entity component system because the first person had sort of done something that was almost that, which we actually got, the entity component system, which I'm not even saying is a good design or not. I don't even have an opinion on something like that, to be completely honest with you. But I think it was a really cool idea and an interesting architectural idea to explore. And so I'm really glad that we got there either way, but I wish we could have gotten there a little bit sooner. So unfortunately, the mistake, if that's 35 years, it does unfortunately not end there, because if you do a search on Google right now and you're like, I need an OOP tutorial, I need an object-oriented programming tutorial, what will you see? Hit number 1 will have a domain model that has encapsulation that matches, you'll have a compile-time hierarchy that matches the domain model.
This is just an example for like kids who are learning how to code. It's not. This is again a strawman. Like when you are teaching programming, you are starting with simple metaphors. It doesn't have to be, all professional and perfect design, from the first lesson. It's about basics.
Exactly like we don't want. This person imagines, this is the number 1 hit. He imagines something called a special Iron Man that's slightly different from a regular Iron Man, because I guess in his mind, or whoever wrote it, I don't even know, it might be a team of people, there's some kind of a specialized Iron Man that I don't read comics, maybe that's a thing. Hit number 2.
There are specialized Iron Mans, right? If you watch Marvel movies. Okay. We have our automat here, and I should be able to crash it now by zooming in. 0 to 4,000 again. Okay, seems to work. I know what's wrong. So my code is writing over other memory, like the memory of. This is a classic like C++ error. This stuff wouldn't happen in any managed language. It wouldn't happen in Java. It wouldn't happen in Rust.
Hierarchy that matches the domain model, but it's one of the ones that you can actually find in those early papers. Shrusup talks about vehicles sending cars, and if you remember, cars crossing a bridge that could be trucks or buses was in Simula day 1. It's where they came up with that subclassing thing that they were going to do. So we're still pushing it today on hit number 2. Hit number 3 is 3 types of bicycle that come off a bicycle, right? And don't ask me why there's spaces in that and not in the mountain, but I don't even know. That's the top 3 hits. I stopped looking after that because I'm just like, I give up. So one thing that we could do.
This is just, again, nitpicking. He's taking tutorials intended for kids and he's criticizing them because they don't use some game dev tricks for optimizing performance. What is this supposed to mean?
To keep this mistake from propagating is just get this idea out there that compile-time hierarchies of encapsulation that match the domain model are not that good. Sometimes they work, like with distributed systems or maybe microbiology, but a lot of times they're just more work than they're worth. And that would help. It would help a lot. And I would bolster that here at finally the end of the talk with this quote, which I think is the best one to end on. It's that the most treacherous metaphors are the ones that seem to work for a time because they can keep more powerful insights from bubbling up, right? We got this thing in place. There was this compile-time hierarchy that matched the domain model idea, and it was stopping all of our other architectural development because everyone was saying it was going to work and it was going to be great, and we just must be doing it wrong, right? But actually, that wasn't the case. And this is a hard quote to find. If you search for it, I'm not sure if you will find it, but if you read through, you will find it. It comes from Alan Kay. He's the one who said it, right? That's him sitting at his, I think that must be one of the original Palo Alto computers, right? The Alto, I think is what that one is, from Xerox PARC. So that's the actual end of my talk. Thanks everyone for listening. I'm surprised I was able to remember all of that stuff for this. You've been a wonderful audience. And I guess now Ryan Fleury will be coming up on stage to interview me and take questions from the audience. Is this correct? Sam?
What?
Sam, is that true?
I say it again.
The organizer, ladies and gentlemen. Please welcome to the stage Ryan Fleury, everyone.
Okay. Well, yeah, thank you for that talk. That was really good.
It was a lot of fun putting together.
Yeah. So, I guess the first comment that I would have is that it seems like I'm a little bit glad to see that people in the there's two things. I'm glad to see that people in the 60s were like using these techniques that seem to be reemergent. It kind of makes it feel like there's like maybe like some degree of gaslighting since then. Like there's like all these, you rediscover these things, they seem to be useful. And then for some reason, like we haven't actually, that information has been lost, I guess. Do you find, I mean, I assume you find the same thing to be true.
It was never lost. It was always there. It's just, I know, I feel, honestly, I don't mind like working with triple code, bad code. Like usually it's kind of interesting to look at bad code. Hey, this is also a nice presentation. When a display draws something different all the time, also looks kind of cool. Nice. Anyway, those ideas were not lost and not rediscovered. Those ideas have existed since before programming became a thing. It's about how we decompose objects, how we decompose problems into objects.
Yeah, I mean, I guess the problem, so I don't even know if it's like gaslighting in that sense, right? Because it's like, I don't necessarily know, I didn't find a lot of evidence that people were like intentionally, obviously, like it wasn't like somebody was like, I would rather promote my thing than this thing in Sketchpad that I noticed. That quote from Alan Kay is kind of instructive in this case. He honestly believed that having the thing be omniscient was bad. He's saying that this is bad, right? And you see the same thing from Strustrip saying that this, switch, this basically switch on a type is bad. And so I think they just honestly believed that. They believed that these were bad for modularity, and in their minds, because they're so focused on the modularity, they were just saying this isn't good. And so it just kind of doesn't get propagated. This is the thing that you see all the time, right? If someone isn't good PR for their thing, it doesn't get propagated.
Yeah, that makes sense. So, in your own personal programming journey, you started with learning the traditional object-oriented sort of, or C++ templatization of compile time, hierarchies of encapsulation, and so on. I mean, I have an idea of where you changed or where you developed, but I'm curious about where you learned to not do that, and furthermore, from where you learned it, where did they learn not to do it? Did they learn from the original papers, or did the simple ideas just reemerge, or what is the story there?
So that's kind of interesting. So when I was younger, so when I started programming when I was very little, right? I didn't know any of the things. I wouldn't know anything about architecture. C++ wasn't even invented I don't think. Would it have been invented? So C with classes would have been, but C++ wasn't even out in the world at the time when I would have started in BASIC or something like that, right? So I definitely started without any of these notions. But then when I first went out into professional, I mean, my first job was hardly professional, but when I went out into the world of commercial programming, I definitely thought that everyone was presumably right about this. I just didn't know. And so I tried programming in this model and learned all those things because, you know, it kind of has a Magic the Gathering feel to it. It's like you're learning a lot of intricacy, and it's just Magic the Gathering. It's something people made up that was fictional. But you know, you don't know that. You think it's real, right? But you're getting into it in the same way you might get into Magic the Gathering. You're like, oh, I figured out that the template can do this thing. Yeah. And it becomes its own little game, right? So I think it kind of went that way for me. And at the time, it was very obvious that this was stupid. Like if I'd actually thought about it, but I chalked it up to me just not knowing how to do it right, which I don't think was actually true. I think it was just like, no, these are actually just worse than what you were doing. Because what I noticed was things that would have taken me only a few days before were taking like months to like figure out all of the ways that I would have to do it in order to make it fit these things. And I think I was just too stupid to realize that probably just means it's just a bad approach, right?
Yeah, that makes sense.
So you had a second part of the question, which was, how did I undo it? That part is a little more concerning, I guess, because the only reason that happened was I happened to then program with people who had never done that. So they were people who never had the experience of being told to do this architecture or just ignored it and continued to program the old school way. And I was like, oh, these people are very successful and very important programmers. So maybe it's not the case that I just don't understand it. Maybe there's actually something to keeping doing this way. The reason that's more concerning to me is it's like, it means if those people aren't around, if they weren't around, maybe I would never have that experience, right? And so you kind of need this generational overlap of people who still remember the good things about the previous way to tell you that the new way kind of sucks, right?
And do you know, like, when you worked with those other programmers, were they informed by this older generation, like the 1960s papers of how they were doing these things? Did they just take those lessons, or
No, I think it's just a case of like if you were using programming resources from that era of even just the 1970s, you wouldn't be seeing, like, it was more academic, the places where OOP would have been talked about, right? Smalltalk was a thing that would have been in research stuff, right? And Simula was a thing with papers and stuff like that. But the person who learns to program, like, you know, in the game industry and stuff like that, the person who learns to program on an Apple II is not being exposed to those things, right? So they just learned in an environment and using reference materials that did presumably kind of come through that culture, but it wasn't like they were, you know, nobody was like, oh yeah, Doug T. Ross, man, and plexes, like that's the stuff, right? It's like, no, like, so I think it's just more that they hadn't have had that idea pushed down on them in a way that they believed.
Okay. So I had it in my head, but I got to check my notes here. So I think that I was curious about, I have a collection of like not exactly related questions or discussions. Like,
Hit me.
So one of the things, you introduced this subject by saying like, one of the arguments that people will use to promote like sort of object-oriented these, or I shouldn't say object-oriented, I should say compile time hierarchies.
If someone out there wants to come up with a catchy moniker for that, it is hard
Yeah,
to say.
right.
So we need something like OOP for that, right?
Yeah.
And it would be nice because, again, like I said, I think it's pretty important to draw that distinction because like Mock, who I quoted
OOP is
in
a,
the thing, who
OOP
did that
is a
in the
nice name
component system,
for this. It's a perfect name for this.
Like he's thinking of it in terms of object-oriented. He's not thinking this is not object-oriented, right? So you can easily call yourself an object-oriented programmer and want object-oriented principles to apply to your code base and just not think about that compile time thing. And it seems to work pretty well.
Which,
Yeah, kind of see.
again, almost nobody does this the way that he criticizes. Like he's criticizing a very narrow category of programmers, like almost non-existent, I would say. I don't think I've met anybody who would do this seriously in my whole life.
Seemed like the object
It's always like an internet meme that you never actually encounter in reality.
oriented part of drawing boundaries, it doesn't actually, it's not, it might be descriptive of a system, but it's not prescribing like where to put those boundaries exactly.
Yes, exactly. And also, furthermore, it's something I think we could all agree about, right? I don't know that a hardcore object-oriented person, like certainly not Alan Kay probably, would never agree that making like an API boundary around something was that object-oriented if the thing was fairly large, although he might. But we can all agree that that's a thing we want to do. Like, I don't consider myself an object-oriented programmer, but I consider that to be a good thing to do. And I think that's certainly a point of commonality. And I think most object-oriented programmers would call that an object-oriented thing to do, even though it really predates that. you could just think of object-oriented programming. One of the principles is sort of crystallizing that idea into one of their core concepts. And I think that's a good core tenet to have, right? To do that at the appropriate size. That's where I tend to part ways. It's like what that size is.
So on the large team subject, you were digging through all of these historical papers and records and everything. Did you actually find any research about what people actually do for large teams?
So one of the things is I was focused on figuring out where these ideas came from. So I didn't go looking for where the, I don't want to call them excuses, it's too disparaging, but where the justifications came from, right? So what I can tell you, so I don't know, that'd be a whole nother talk. This thing took 2 hours or something like that, right? So that's a whole nother question. It would be very interesting to answer. But what I can tell you is during the course of the development of these core ideas, I never once saw anyone talk about that. And there were always like one person doing a thing by themselves, or two people developing things by themselves. And to the extent that like larger teams would have been involved at all, it might have been on the Simula side. Like some of their opinions may have been influenced by, in ways that they didn't directly, like they didn't attribute any of those things to it, but maybe they were seeing people use Simula out in the world that had something to do with it. But I don't think there were that large teams working on Simula either. I don't know.
Yeah, it's kind of interesting alone that the history of computing, it's always large team or small teams pushing large improvements like successively. So it's interesting to optimize for large teams in that way. But
well, and you might even say it creates a bit of a problem because it means that like if the innovation happens in small teams, but we do need large teams of people to do certain things, it's like it's kind of hard to figure out where the innovation in that comes from, because if our other risk comes with these few people doing something, they're not having the same experience as a large team. So maybe it's like small teams doing something on the side of a big team is where we get some of that innovation. I don't know.
Yeah. So I'm kind of curious about a few programming ideas that a lot of people use, like that you regularly use in your programming came up. One being like discriminated unions or tagged unions as sort of like forming this like mutually exclusive branching structure, as opposed to like the fat struct model where it's like it's one unified type. I'm kind of interested to hear like what you think about like. Both of those things you've said are like good in their respective situations. I'm curious about like when you know that introducing boundaries of mutual exclusion, like in a discriminated type, is useful, whereas the sort of large fat struct thing stops being useful in those cases.
So I don't really think of them as distinct. I think of them as sort of the same things. I'm just trying to use terms that other people think in to communicate that. So the way that I normally think about it is there are two types of situations I might find myself in. One is where the domain model itself, like literally the thing, is telling me clearly that these things are mutually exclusive. And that might be a place where I, have more in common with the OOP side of things. So I'm like, I see why you guys would think about if that was true about this thing. So in those cases, I would use a discriminated union because I prefer to write code in like a verb-oriented way, not an object-oriented way. But I'm just doing the flip side of what they're doing with their virtual function in those cases, right? I just think it works out better in my way, but that's just, that's my personal opinion. It also has to do with what type of system you're making, whether or not people are going to be adding types to the system more frequently, or whether they're going to be adding actions. I tend to find that people add actions more frequently. That's why I focus on that. But either way.
That makes sense.
So if I can see that this is by definition mutually exclusive, then I'm discriminated union. And the reason for that is the exact same reason for Strustrip and everybody else, to catch errors. I don't want to make that a fatty struct where I'm accidentally doing code that's going to do both things. So I try to basically replicate that Simula style thing, or really it's Tony Hoare's, right, Sir Tony Hoare's idea of that. I try to replicate that, and it's just unfortunately C++ doesn't really have good support for that. Like I said, standard variate's not very good in my opinion. The real thing that Tony Hoare wanted would have been great. So I would love that feature. The fatty struct qua fatty struct, and like I said, I mix these two together, so I don't think it's that distinct to me, but the idea of like feature flags or something like that, right? Like I'm gonna hit this bit and then it means that this path might be taken. What the Plex guy, right, what Doug T. Ross would have called those like switches, right? That to me is for mix-in, as they call it, right? When I know I'm combining lots of things together, right? Like a tasty stew that's gonna be delicious and it's gonna taste fabulous when you use these entities, right? That's when I reach for that. And I think those are they're very simple. You can teach them to someone in an afternoon, and they can apply them pretty directly right away. And that's one of the reasons why I think they're so much better than things like the compile time hierarchies, where I've seen programmers tie themselves in knots and spend months trying to do something that literally that approach would take them 30 minutes.
Yeah.
Right?
Yeah.
So.
And I'm a little confused about the exactly what. So Looking Glass, you introduced them as using like sort of the fast struct model, but it sounded like they ended up with an entity like component system thing where they split everything out into like they pulled out common parts of entities and isolated their storage. Did they make that transition, or did they use one early and then the second later?
Can I ask a question to the audience?
Yes.
Sam, how much time we got?
We still have time right now. Maybe, well, it depends. There are multiple paths that could be taken, and the split point is in about 25 minutes.
How badly do you want a complete version of that answer versus a summary answer? Because I can answer that very accurately.
Okay. Yeah, let's go with the accurate one. Okay. All right.
Deleted scenes to keep this talk somewhat under 2 hours, which hopefully we did and now won't do. So I'll skip some of this just to keep it relatively quick. So inside Ultima Underworld, an entity was basically a fatty struct overlay. So the way that it worked is you had an entity, and then if there were two separate things like hit points and fuel that were generally mutually exclusive, meaning an entity probably can't have both of them because fuel is used only for like lanterns and lanterns don't have hit points, then we'd put them in the same place. Okay. Right? That was Ultima Underworld, right? And of course, this is rough because it's like it means that when you're accessing one of these, you're secretly also accessing the other, right? Because they're in the same place. And so you could have an error where you were doing something where like you're checking the fuel or you're checking the hit points. In this case, like you're checking the hit points, but you're secretly checking the fuel. Yep. And then you delete the entity, because that's what it was thinking, right? And this is Mock. His picture didn't make it in. I'm glad I get to show him now. He's the guy who did a lot of the implementation on the dark object system. He came on the scene in Ultima Underworld 2, and he's the one who coined that phrase, that quote I put up. That's him, the compile time hierarchy. He's the one who crystallized that, right? He comes on because in the earlier ones, like it was Doug Church and Dan Schmidt and a bunch of people who did Ultima Underworld 1. He comes on Underworld 2, and he actually literally had that bug, that fuel bug. He wrote a thing for damage where if you threw an empty lantern at a wall, it would enter the damage system because it was supposed to take damage from hitting the wall, and it would be like, how many hit points does the lantern have? It'd be like 0. It's like, well, I guess it's out of here. And so empty lanterns thrown at walls would just disappear. Nice. Right? And so he had to fix that bug by doing exactly what you'd expect. He'd have to check, you have to manually add that code. Yeah. And so, they didn't like this. Because remember, these guys, and again, much like, Ivan Sutherland and Doug Ross, these guys were super smart MIT people, and Sutherland was also Carnegie Mellon and Caltech, right? It's like kind of nuts going through the whole gauntlet there. The folks at Looking Glass are MIT graduates. They're super, super smart guys. They do all this amazing stuff. So they don't want to have this happen, right? They just don't know what else to do because they have these like really hardcore memory constraints. Yep. And furthermore, they talk a lot about the sort of trade-offs you have to make. So if you have a fuel system that needs to store stuff and you have a combat system that needs to store stuff and you do make space for them, it means that if you do, if you're using that overlap, it means that if you then decide you need an entity that has combat and fuel because we wanted to add that, it's like, crap, I've got this overlap, I can't do it, so now I have to make a trade-off. Like maybe I shrink the amount of data that the combat system can store, and that sucks, right? Because now I'm forced into this decision I didn't want to have to make, and that's just what the kind of situation they're working under, the kind of constraints they're working under. When they go to do System Shock, which is the RPG, so they do Ultima Underworld 1, 2, and they do System Shock. I'm just following their lineage. They have Terra Nova and Flight Unlimited, which I won't cover because they're not the same in terms of like lineage really for the teams and how they were doing RPGs. This is just the RPGs from Looking Glass. So it kind of looks like that. I'll skip this because it's not part of talk. They go to an outlinking kind of structure. So what they do is they say, all right, we kind of want something better than that. So what we're going to do is we'll have our entities. We have a little bit more memory to work with now. So we'll have the entities have their shared part up front that everyone roughly has. So it's kind of fatty, but not that fatty. And then everybody gets one pointer out to something. right? And we'll try to make those things be things that don't have to combine together. But it's still a limitation, right? Because they can't have two of them, which they would have liked to have had. So that's how they got there. That's what System Shock was. It was like one outlink per entity that could extend it.
Got it.
And now that solves their growing problem, right? It's like we can just grow things arbitrarily and they don't like overlap some unrelated system or something like that. Yeah. But it doesn't really allow them to combine them in that way that they would have liked. So it's still almost the same limitation. It's just more of a memory optimization at this point, right? Okay. But it also catches this error, because now you sort of have a discriminated union going on, so you can't access fuel off the base entity because it doesn't have it, so you have to do something like this, where like if it's a light source, I can get the light source, or better yet, I can only return a light source pointer if it was a light source, and so then it's kind of more foolproof that I can just check one pointer and good to go, right? Again, I'm blowing through these, but yeah, this was me making fun of standard variant, yeah. Flight Unlimited, I'm just going into this because it sets up the entity component system thing. Flight Unlimited actually had, it was the first thing to use C++ really heavily in the company. And so they were using new and delete like you're supposed to do in C++. And unfortunately, that totally fragmented memory, totally like thrashed out memory and fragmented memory. So I don't know if this is well known, but basically Flight Unlimited is a game where you like fly around, you know, in the thing and whatever. It was a very popular flight sim at the time, actually. And you'll notice that in the cockpit here, there's gauges, but there's no fuel gauge. Right? There's no fuel gauge on there. It's other stuff. There's no fuel gauge at all. But sometimes it would say out of fuel. It would just be like out of fuel, right? And what out of fuel was actually the memory's too fragmented. So what it would do is it would say out of fuel. It would it had like an executable that was sort of running as sort of a batch restarter for the main executable. It would just close the whole rest of the executable. So it would save the game state, close the executable, reload the game state, and then you're back to good. This is Tom Leonard. So Thief the Dark project comes on the heels of this. This is Tom Leonard. He's actually the guy who, as far as anyone can remember, that I've been able to get a solid story about. He's the guy who actually comes up with the idea of sort of the entity component model switch. And I didn't really call it, again, too much stuff getting cut that we're going into now. So I guess 6 of one, half dozen of the other. But the idea of saying, okay, instead of entity.get hit points, we're going to say hit points.get entity. This is a big, that's a big switch if you've never thought about it before, right? He's the one that, Mock says, I think it was Tom who came up with that. And the reason is so that the types line up. It's like now, instead of having either...
I mean, Casey seems to have an obsession about people who came up with things. I think people who came up with those things didn't publish their code. I mean, there are probably plenty of industrial, commercial applications where all sorts of design patterns were invented, and they're probably still there. Somebody might find them eventually, but most of those design patterns are so obvious, and you can tell this because at the moment that computers became sufficiently powerful to execute those ideas, people started doing this. It only proves that those are obvious ideas.
Tons of functions like get a hit points thing, get a this that are on an entity, which would suck. Now we just ask the actual thing, the hit point system, and it's only going to return one type, which is like a hit points type to us, right? And so anyway, this is what they're thinking about when they make the entity component system, and it comes from all of those experiences that they've had. They want to avoid fragmentation because they just had to make a thing that restarts the game, right? Which was Flight Unlimited. They want arbitrary sized properties, right? Because they don't want to make those trade-offs between combat systems and fuel and whatever. They also had additional things, which is they wanted designers to be able to create types at runtime, so they kind of want bags of properties that they can have designers create. And they want designers to be able to do things like create domain model hierarchies in the editor because they're thinking in terms of the domain model, and it's just not implemented that way, right? So they do those things. And then finally, the how fast is the fastest case thing, that was from Doug Church. He was like, okay, if we're doing all this pie in the sky stuff, we have to figure out some way that it's still gonna be as fast for physics compute and stuff as what we used to do. And so what he did there was he was basically forcing them to go, we have to consider some way that this is all gonna work. And that was the system boundary drawings part. So that's the really fast part of this. And by the way, this is what it looks like inside the dark object system. If you wanna create a property type, right? It's, like I said, it's still OOP looking, right? Like you could pass this by an OOP person and they would be fine with it, I think. So it's again, not OOP, it's just not that hierarchy thing, right? Yeah. So there you go. I think that's everything.
All right. Let's see what else I've got. Yeah, so I guess one interesting thing about what you were saying is that what it has to do with like the object-oriented, the original object-oriented work came from these like distributed systems and everything. And I know you've talked a lot about in the past like Conway's law and how like introducing these boundaries, or it's not introducing these boundaries, it's the fact that when these boundaries arise, they cause friction or difficulty. And I guess
Conway's law, for those who don't know, is that the architecture of the system resembles the organizational structure of the company that created it. It's not always true. Sometimes it's the opposite. You know, sometimes when you want to design a big system, you have to organize your company around it. So it goes both ways. But this is what this Conway's law means.
Would you characterize this object-oriented thing as like creating those boundaries unnecessarily? So they didn't arise from the problem, and so they're causing difficulty in that way.
I would sort of say that. I guess the only like caveat I can think of there is, I think that the part where you said the problem arise, like the problem doesn't arise from it or whatever, or the you know, it doesn't arise from the problem, I think is how you phrase it. I think a person who thinks in terms of object-oriented programming and is an aficionado of that would claim that it is arising from the problem because the domain model looks like this, right? And so I don't agree with that, but I don't know what they would agree with, right? And so from my perspective, I agree with you. These are things that just because as a human, you're going, I like to categorize things into groupings because that's something that we do, right, linguistically. It's all quantum physics at the end or something, right, bro? So it's like, these are arbitrary categories that we're drawing. There's no reason to think, you know, just like I don't think the laws of the universe think of you as Ryan Fleury in a computational sense, but I think of you that way. It might not make sense for you to have the computational version of Ryan Fleury be about Ryan Fleury instead of just a collection of things that produces to the end user the effect of Ryan Fleury, right? So to me anyway, that's sort of the difference there, right? It's like, I don't see that the model inside the computer may have very little to do with the model experienced by the user, which again is in direct conflict with like what Alan Kay wanted to do. He wants, and again, you have to remember the mindset. He also he wants to do education. He wants to teach people about computing. He wants it to feel like you're programming in the same way that you see the real world. And in some ways, I think, if we could just get to the point where, and maybe he does think about this now, I'm not sure, just get to the point where he thinks, oh, well, that's just when you use an application. That's what it feels like. It's not what it is under the hood. Right. Then I think I'd be right there with him, right? Yeah. So, yeah.
Interesting. All right, I'll check my list, and then maybe if anyone in the audience has questions, then I will ask. But I'll check my list first, since I'm up here talking about it. Okay, I had 2 pages. I did that one. Oh yeah, I guess another thing. So I guess some of these are like not exactly questions, but they're like, I formed a mental model given your talk, and I want to run it by you and see if it makes sense. So another thing that I guess is implied by introducing these boundaries between parts of your program when you could have not done that in the architecture, but you did for one reason or another. The interesting thing is that you were talking about is it Sketchpad? Yeah, Sketchpad. You have some layer which is like quote unquote omniscient, like it knows, it has full context of what's actually happening. And in my mental model, I'm like, that's similar to when like an actual like civil engineer or something is like going and building a bridge. Like they're not like, how do I build a bridge without knowing what the landscape looks like, kind of thing. So it's like, so a lot of the design decisions in C++ or in all of the other paths that you iterated, it seems like they're about like removing context or trying to find the minimal set of context. But I assume like that doesn't seem helpful. I haven't found that to be helpful because of what you have taught, basically. But I'm curious.
I kind of feel like you're on your own orbit now, and you totally know exactly what it is,
Okay.
right? I mean, like, yeah. Honestly, you're one of the best system architects I've ever seen.
Oh.
Full disclosure,
Gee,
right?
well, thanks.
Folks at home, seriously, like, it's insane. So you don't need me to tell you what to do.
All right. Well, thanks. I appreciate that. But so I guess you know, I think that's probably it. I'm having to turn through these 2 pages here. But
Well, to answer that question though, like
Yeah.
about like removing that context,
right.
I do think like that's part of why it's frustrating to maybe look at the history a little bit.
Yeah.
Because what it looks like to me from like the bird's eye view is like, instead of asking how do we achieve code reuse and modularity while preserving our ability to solve the hardest problems, it looked more like it was like, let's just redefine the problem to be simpler and solve that.
Yeah.
And to me, that was one of the big things about the Sketchpad thing as well, where it's like, okay, you had working examples of this that are pretty well documented. I mean, if I can go figure out most of it now, looking back, then at the time when you could have actually talked to Ivan Sutherland fresh off of the implementation when he remembered it all, right? Yeah. And so it does really feel like, I feel like there's a failure to engage with the hardest problems. And I think one of my takeaways from it, which, you know, from reading the history, which is not, it didn't really change my mind about this, it just reinforced kind of like my feeling about it, which is, I think when you're designing new things, you should focus on the hardest stuff. Yeah. You should say, what solves the hardest problems? Because we can always then take that and scale it down and remove things from it or dumb it down for people to use in cases where that aren't as hard. But it's almost impossible to take something that only solves simple problems and scale it up into something that solves hard ones. And so that's really the thing. And I don't blame anyone in this that I covered here for that at all, because the conditions they were working under are awful, right? I mean, they have none of the benefits we have today. They were working with computer systems they barely got time on half the time. Yeah. It was hard to debug programs, all that stuff, and they're having to invent all this stuff themselves, right? They have nothing to fall back on. So it's nobody's fault, but going forward, it's like, when we have good tools, let's attack the hardest problems, and that will be where we get our really good architectures. That's my feeling about it anyway. Yeah.
Do you blame Y Combinator at all for like the internet?
I'm about to blame them when I see what they post about this talk and somehow manage to miss all of the good arguments you might have about it and argue about something else, like whether or not that was the right use of discriminated union, which 100% will happen, right? And you're just like, guys, who cares? Like, that does not matter right now, right? But okay.
Yeah, because I think like actually programming, that tends to be one of the harder problems is well, I don't know. You've said it 100 times already in the talk, but where you draw those boundaries, because it's not that modularity stops being useful, it's that it's a wall you're introducing that makes something more difficult. And so if you put that right into the middle of the hard problem, like you say, yeah.
And I think that is the fundamental struggle. It's why architecture is so hard. And it's also why architecture is potentially difficult to reuse. Architecture, not like reuse inside an architecture. Right. And it's because when you draw those encapsulation boundaries properly for a particular problem, you save orders of magnitude of work when you do it properly. And where you draw them could very well be different for different types of things you're trying to solve. And that makes it hard to say, okay, here's an architecture that just works across things. Or one of the reasons the compile time hierarchy thing I think is a bad idea is not just because I don't think it's very useful in general, but it's also because it's Procrustean. It's like this one size fits all approach that I don't think really even fits that many problems, but it certainly doesn't fit all problems, right? And so teaching architecture, I think it would be better to focus on more flexible thinking and thinking about drawing the encapsulation boundaries with intent, not with a fixed model in mind. And if that intent leads you to a very unusual placement of the boundaries, as long as you can prove that it's actually getting you that leverage and not introducing cuts in places where it makes programming difficult, then you should do that. You should follow that sort of weird structure, because that is probably right.
Yeah, no, that makes sense. Okay, well, I think I've exhausted all the questions or discussion topics, or they would be rehashing things that I wrote them down and then you covered them in the talk, and I was like, oh, okay. So I'll ask the audience. Does anyone have?
Should we just cut now? Is that good time to stop? Because
well, we can do one. We have maybe 5 minutes.
Okay. Shoot. Sorry, everyone. Okay. Raphael, do you have a question? You can just speak out.
Yes.
Like, if we had the solution in the 60s and we saw the power of like Sketchpad and like why was, let's call it dark OOP, still able to gain foothold and catch on and suppress the good solution? Was it a succession or knowledge transfer problem, or was it just because dark OOP is such a category of programmers?
This is actually the question I had very early in the beginning. He said that neither Simula nor C++, none of them encourage this behavior. And I guess it just comes from how this dark OOP is a strawman. It doesn't happen in practice. Usually when somebody learns object-oriented programming, their first program that they write usually abuses the object-orientedness. This is when it looks like that in a silly way. But this is just the first program that everybody goes through. After that, you realize that there is no point modeling everything as an object. It's just a waste of time, so you don't do it. So this whole thing, I think it's just a made-up programming methodology, but almost nobody programs like that.
A lot of interesting problem. How do I represent that, or was it something else? Like, why does it catch on?
I mean, it's very speculative to try and guess something like that, obviously. I think you touched on some of the answer there, which is that, like...
I honestly would love to see some examples of those terrible programs being used in practice, and I think all of them will turn out to be just programmers who are just trying object-oriented programming for the first time. They don't know how to use it, and they abuse objects to model real world. Because, I mean, I don't know any example of a program which would actually suffer from this issue. But a lot of people are talking about this like it was a real problem.
I do think people want to divide things into hierarchical categories kind of naturally. I mean, we did that with the natural world when we were trying to do biological classifications long before we had really any basis to do so, like before we knew about, DNA or anything like that, or how, those things might have happened. So I think it's a natural thing for people to want to do to make those classifications. So there's some of that. And thinking that there's this easy sort of model that just goes from what you see. It's like WYSIWYG architecture. Like what I see in the real world is just what the code looks like, and we're done, right? So I think there's a little bit of that, but I think the real story is just that history is very messy, and in order for something to gain traction, somebody has to champion it. Someone has to do the work of implementing it into a system and doing a good job of that, right? One of the reasons we got the sort of compile time hierarchy thing is because that's what Strustrup kind of took away from Simula. It's what he implemented first into a language that became very popular. And he wasn't trying to do anything nefarious, right? He wasn't trying to do anything dark. He's just like, I like this type checking thing. I used Simula, it was kind of cool. He did the work, right? I mean, you could say that about things that we see happening today as well. It's like, in order for something like, Rust or something to gain popularity, somebody has to build Rust first. Somebody has to have an idea of what it's going to be. Is that idea good or bad? Who knows? But in order for it to even get judged in the marketplace, someone has to do that. And the bottom line is, nobody who looked at Sketchpad was thinking in terms of architecture other than what I said, which is like virtual dispatch, basically. And, I didn't go into the talk, but Alan Kay was predisposed also to think about that virtual dispatch as being very important, because the other references that I didn't mention, but they were in that quote, I said we're not going to cover them. They're like the Burroughs 5000 series computers, and there's this Air Force, this guy who wrote a file system thing where you put the way that you use the files in the file system were subroutines that were stored in front of the files in the file system, so it's kind of like a virtual dispatch thing. The Burroughs 5000 system also had this kind of virtual dispatch where there were tables and things. And so for Alan Kay, who we didn't really cover in here, the other 3 hours of slides, they're all there, right? But what he actually was seeing was he was seeing commonality there. He was like, oh, the Burroughs 5000, that Air Force thing that I thought was cool, Simula and Sketchpad are all doing this dispatch table thing, and they're all making classes with these dispatches on them. And then he's thinking molecular biology and this messaging, you're going to respond to these messages. That's what these dispatches are. They're how you're responding to different messages. And he just goes down that path because he's thinking that that's the core thing, right? Because he's predisposed to see it because he's encountered this idea multiple times. And so he's predisposed, I think, to think that that's where the power of Sketchpad comes from. Because like, let's face it, would we have recognized that power at all if we hadn't had all of this experience? And like, you know, I just randomly kind of stumbled upon this, like, oh wow, wait, okay, like that's really kind of interesting. It's if I had never seen an ND component system before, would I ever even have thought of that? Probably not. Yeah. So I think it's really hard. It's a really big ask. It's a tremendous ask to ask someone who's like inventing C++ or inventing Simula to somehow get all of that. It's just not plausible. You know, it's not plausible. It's a hindsight thing, I think.
For sure. Oh, we have a question right here.
So it seems to me that the pattern is always the same. Like you kind of come from school, it was my pattern too, and it seems that it's yours, right? You learned a certain way. And in school, everything's kind of tied to business stuff, right? So it's very easy to think about, you have a client with an invoice with items, right? And usually it doesn't go that deep into very high hierarchies, but we kind of just learn that pattern. And then we just start using it, and you have a hammer that is a melee weapon, that is a weapon, and whatever, right? And then we have to have the luck of finding somebody along on our path that kind of snaps us out of this and shows us a different path. But also, these people are kind of disappearing from the industry. So my question is like, how do we fix this problem? How can we improve this? Because it kind of feels like you're trying to get smokers from stop smoking long after they're smoking, you know what I mean? So you're...
Well, I guess I would say you're at the right conference. I mean, that's all. Right? I mean,
Circuit making games are always nice. This is like, it's what programmers do for fun, right? We play games like Factorio.
I don't know. You start doing stuff like this, and you try to go through the history and show how it happened and stuff like that. And that's it. You know, I mean, that's the best you can do is put these ideas out there. Suffer the Hacker News thread that you will then have to endure, right, or whatever else has to happen. And then you hope that maybe some of those ideas get picked up and people think about it more critically. I think we're out of time, correct?
Yeah.
There is coffee. We're going on break now. We'll be back at 20 past for Dennis.
All right. Well, I hope I will be in the audience anxiously watching this talk. This is from Teardown, right?
I think so. Yep.
Okay. I'm excited to see this one. I'm really looking forward to it, Dennis. All right.
All right.
So
Thank
we'll
you so
be back
much,
here at
Casey.
20. Thank you, Ryan.
Yep.
Overall, it was a nice presentation. I wasn't... I still wonder what was the point, because if you go back, you know, in history, you always arrive at very early attempts at philosophy. So I don't know why Casey decided to stop in the 60s, why didn't he went back? Because there are some developments of the original object kind of idea that philosophers made that are also interesting. There are this idea of monads, right? For instance, that Haskell has, sorry, not Haskell. Haskell. The ML languages have them. It also comes from philosophy. It's not a strictly programming invention. It all comes from, you know, people who were thinking about those things long before computers even came on the stage. Okay, I need to redesign this tree because... and I don't want to overcomplicate it. Yeah, monads. If I remember correctly, a monad was the answer to the identity question. I think Hegel introduced it, and I think the idea was that it's some kind of indivisible essence of an entity. I may be mixing stuff up, so double check me. I'm not a philosopher. I just got introduction to philosophy. No, I'm not familiar with numens. This idealism is this the oldest idea in philosophy, coming straight from Socrates about this. This is about this cave analogy of ideas and reality being a reflection of ideas. Yes, so Leibniz's monads are simple, indivisible, each reflecting entire universe from its own unique perspective. Okay, now it becomes crazy. Yeah, for Hegel, the monad is an updating thing. Which is exactly what it is in ML languages. It's a way to capture side effects. So you can see those ideas they are fun, and I think philosophy is a treasure trove or more ideas for how software could be designed. What's numen? I know numen comes. Change the language. Divinity. Interesting. Maybe this is where Tolkien got a name for Numenor. At least this is how how the name kind of sounds to me. It sounds to me like this continent from The Lord of the Rings. Okay, I think I will remove templates. I think templates were a bad idea. Or maybe I'm not actually doing too much with those templates. So instead of default value, this should be called different. This should be called neutral value. Because that's the point of this neutral value. It shouldn't influence the result in any way. So I would say that our tree is only going to do min-max. That can answer min-max type queries. Nice. Okay, it may require some more funny code. Let's see. So of course I will have to delete origins. How many of them do I need? I think n. N is definitely going to be safe. I don't need to store them for the root values, leaf values, because the leaf value position is its identifier anyway. I think I will need +1. But here we don't need this extra element. Okay, I think here I can also do this -1 trick, -1 +1, because I will never access the value number 0. Let me think for a moment. So in a tree like that with 4 values, you only need 3 nodes. So actually this could be -1. Yes, I will fill this with -1s. That's great. Okay, instead of config op, I will have config test, which will return bool. So I'm using this a lot of bit tricks where 1 means right. So this is why true means right for me. Now I need to implement those tests. It should look like that. And actually I cannot access these origins of node. I need to do a check. If node is greater than leave begin. Otherwise, cool. And now we also need to fix our query function. It should ideally, I mean, we don't need to return t actually, because it can be accessed from the tree. We just need to return I. This is interesting. I actually don't need to keep those values for intermediate nodes. I don't want to overcomplicate this. I mean, I could totally remove the tree from this structure. Could keep it outside and just pass the pointer, and the tree only needs to create this array of origins, which is much smaller. So this query should return the index of the smallest value. I need to also convert both of those. And this one. Result base plus R, plus R, check. Okay, all looks good. I think the tree should now report positions. Oh, this is actually wrong. Oh no, this is fine. Just return value instead of returning result. Should return result origin. Let's not do hacks for a moment, so that maybe it will work. It's kind of getting late. I'm not sure if I will finish this today. But this was supposed to be something really fun. This is what will actually make the displays be very clever. They will appear like they know what... They know the natural division of mouse trace into components. I will have to take a look and see why the debug build is so slow. So slow to build. Okay, node has this number. It's a very high number, by the way. Leave begin is 8,000? Okay, so I've allocated only something doesn't look right. Oh no, maybe it is right. I do not record the original size. Was the analysis size? Yeah. 4,800. Okay, this is fine. Oh yeah, yeah. I need to allocate a little bit more memory. This much memory. Oops. I know, so C++ has those foot guns, but they are kind of fun. And they make programs really fast. Okay, found gap, we get index now. The gap. And the program can lock sometimes. Let me run the, sorry, no, debug version. I want to see where it gets stuck. I can scroll and I can zoom in. And now Automat got stuck. I can pause it and see what we are doing. The renderer probably is stuck. Okay, be right back. Fascinating, we are in the we are stuck in the query function. Huh. It's step is equal to 32. How could this have happened? What were the original L and R? I wonder. Let me try again. I can already see some improvements that we can make to the tree. For instance, we can ignore result. We don't need result. We just need the origin. Here when we call test, we will pass tree and in parentheses the original index. And we will not even cache those values. We will completely remove this tree. We will only store n elements now. Step by step. I will not do all of the changes at once. Okay, let's move here and zoom in and pause. What is our renderer doing? So original L was 0, original R was maximum. Wow. Display.startI, display. This is probably the... I see this as well. This is probably the NVIDIA drivers. I mean, at least for Automat this is the case. This is NVIDIA drivers just initializing connection to the device. That should help. Actually, no, it's not going to help. I don't know what it's doing, but it's a weird thing. It just happens. We are still getting stuck. Yep. It's just, I don't know. I have no idea why it's so unoptimized. Maybe they don't care about app startup, because this is not what benchmarks care about. Whenever somebody benchmarks GPUs, they usually compare how low the FPS is once the game starts, not necessarily the long black screen before the game even appears on screen. Eventually it got stuck. So we are again stuck in the query. Original L was 0, original R was this. If I don't want the arithmetic, I want bitwise. Okay, so I think after this line we will delete. I mean, I'm not interested in main program. interested in this. This thread. Can I like resume this and pause it? I can. Or not. So the R should drop to 0. It didn't. Why is R still so high? Maybe it's doing some promotion, who knows? R is definitely unsigned. Yes, it is. A single compilation takes like a minute. It's becoming hard to deal with. Once it builds, the performance of the bug builds is kind of acceptable actually. I don't mind it being slow. Okay, we got stuck. See our renderer. We still have the same issue. Step is 32. When we beat shift, this, which I guess this is all ones. We get 0. Okay, this is in other words bit shift modulo. I still wonder how we arrived at this. R can only be decremented here. So I guess we arrived somehow at I mean, I could even try following this path. So we started with 0 and 1 to 6, 8. One 9 6 8. This fails. LN1 fails. This one is 0, so we decrement R. Just trying to follow this. So we went to this. And then we are doing step. We count trailing R's, trailing ones in R, which is, there are quite a few of them, and trailing zeros in L. So this gives us 32, this gives us 4. So we shift both of them by 4. Now R is 1 to 2. Again. We are checking if they are equal, they are not equal, checking if L ends with 1, it doesn't, L was 0. We are checking if R ends with 1 and with 0, and it does. Bin R now looks like that. So we again compare it with the result and decrement it. Now it's 1 to 1. They are not different. Oh, okay, I think I see the problem. We did decrement R so that it should have dropped before L, but L was 0. I can just move the decrementation later. And now it should work. It's nice to have a debugger. This is the problem of using unsigned numbers. They may bite you. Nice. Now I can zoom in and out, and it looks like I'm not even getting any funky results. It's nice. This kind of looks interesting. Looks kind of fun. Okay, can remove the debugging code from here. A few changes I would like to do to this segment tree in a moment, all in due time. This gap. It's actually very nice to get it. I would like to, instead of analysis size, I will just put all of those values in the segment tree. Everything is going to be part of the analysis. Timestamps size -1. Okay, now for each timestamp, I'm storing a distance to the next one. And I don't need this start I or end either here or here. Okay, that should work. I want the indices to be the same between timestamps and the gaps tree. So there is a 3-second gap. I suspect have no idea where it is. Now it disappeared. Guess it's somewhere here. Okay, apparently here are 3 seconds. Oh, actually that makes sense. Here we have 2, 4, 5, something. And there is 5, 6. Okay, 314 makes sense. So our code can find this gap very quickly. So what are we going to do? So I will take the display, this display, and if okay, I will try to split it. I will try to find a gap somewhere within this display. Start I and I minus 1. Good. And this gives me the largest gap within this display, and actually I don't want to find the gap within this display. I want to move from the left edge of the display by the minimum width of the display and from right edge by minimum width. So I need to do this movement. Display min t. So this is the earliest position where we can split it. Earliest split I will be the lower bound, yeah. Actually no, upper bound. Latest split will be this. This will be upper bound minus 1.
Low pass effect.
Terrible names, terrible names.
Low pass effect.
Okay, so if there is something like that, then if the display is essentially small enough, that we cannot break it into halves. I will do this place to draw pushback display and remove this. I can continue. Display has this and I, but this and I is not inclusive. And I is not inclusive. Okay, so this lower bound, it must belong to the left display. So this is the lowest that can belong to the right one. Okay, this gap it makes sense. So we are finding a gap and now I need to check if those resulting displays, if the resulting display is large enough. I mean, it has to be large enough because I moved it by half. So okay. Oops, no, I don't want that many suggestions. So this is the largest gap, so we will split the display in the following way. We will start with start T. It's going to be this. And T will be actually it's -1. I should be able to remove those. If I didn't make any mistakes, should work. If it works, then I can explain it. If it doesn't, it looks like it doesn't work. I guess it will OOM in a moment. Debug. Let's try debugging this. This is most likely stuck in this function. So now it should be trying to render stuff. It probably can't render stuff because we are stuck in some loop. We can pause it, check our render thread and see what it's doing. Doing some funny queries. Are we stuck in the query function? I don't think we are, right? LR. Let's try doing some stepping through this. LNR are different. Advance L. The base tells us at what level of the tree we are. This is level 7 or something like that. This one again. They are different. Advancing L are not so much. The step is still one. No, they are equal. Oh, whoa, whoa. We just tested for equality, right? Ah, okay, okay. That was a bug. I don't know how it worked. This is the main exit condition from the tree. But look at that. Our tree now divides it's not perfect, we should adjust it, but it tries to divide the path into meaningful segments. I zoom in. We are making quite a few mistakes still. But we seem to be detecting the right gaps. Okay, this is an interesting example because I have to start a display here. That's my requirement. So the earliest place where it can end is somewhere here. And because I cannot end the display just in the air, I say that earliest split eye is the lower bound, which will be the next element, this one, plus 1. So I am starting search for gaps from the next element after this one. I think this should be just upper bound here. Yeah. So this gap is not even considered. I actually wonder, maybe it should. Is the time 5 seconds. I will dump some debug info. This should draw some text for us. We should get a better understanding of what's happening. To zoom in, zoom out, I mean, until we see just two displays. Okay, our display starts at 1 second here, it goes to 12 seconds here, spans the whole range. So, earliest split. I will actually save this. Here. And now we can play within Automat and see what are those times that it talks to us about. So earliest split would happen somewhere here at this empty point. Of course, we cannot split at an empty point. We could insert an artificial split here. We can consider this. So the first eye that we find that satisfies this upper bound is this. Cool. Latest split is at 8:06. Which is here. I need to zoom in a little bit. Earliest split is still at, or actually it's a little bit earlier, at 4 seconds, 4.13, somewhere here. Still in the error, so we cannot split the display at this point. And the latest split at 9.42. Okay, this is within this blue block. So I think the split that we are finding, this gap, 30 seconds, I need to remember, it's probably this one here. Okay, I think I need to record gap +1. So this is the index after which there is a large gap. So this left segment should include this this gap. And this one should start from gap +1. Exactly. That should produce slightly nicer results. Very slightly. Hey, it looks like it works. Can now zoom in. So it should now divide some things to work out. It should progressively divide this mouse trace into meaningful segments. I mean, it makes a pause when the mouse makes a pause. So now it divided it into this movement up and then movement down. Movement up, movement down. Pretty nice, I would say. Still, we have some issues with displays disappearing at the edge during playback. Or appearing, right, like now. I think this could be fixed. I had one idea, it's that when I'm doing the analysis, okay, instead of doing this fancy thing here, start T and T, I could actually use 0 seconds here. And T is going to be max track length. And when I am inserting a display, I can check and only insert it if it overlaps with the viewport. Actually, instead of doing this when inserting, I can also do this when I'm popping. If start T is greater than right T, continue, yeah. Now, even when the display disappears, it should... I mean, I'm kind of analyzing the whole... It's kind of like quicksort. In quicksort, there is this optimization, which makes it only focus on the stuff that's visible on screen. Like, you can only sort a range of numbers. For example, if you have a range of million numbers, there is a way to run quicksort, which will, for example, sort, but only the middle 100. And this is kind of what we are doing. We are splitting the range dynamically in a quicksort style. But if a part that we've split falls outside of the window, we just forget about it. So theoretically, I should be able to zoom in still very closely, and that should still work. Let's see. Zoom in. For 14 milliseconds now. The important thing is that those displays are... we can still come up with those displays even though we are scanning the whole range, because we are using this top-down approach. There's one more thing I wish we did, and it's this thing here. There is definitely a better way to do this split here. Restart stream, but I see there are some issues. Okay, possibly Twitch chat was broken, I'm not sure. Okay, I would like to, as a special case, allow breaking displays at a point like this one, in the middle of the space. Should be doable. I don't like that because we don't have enough events. We snap them together. I zoom in. How does it look when I have a single? Yeah, the display always covers 2 points. This is what I would like to fix. So after finding a gap, I guess I can skip this. Seems to work now. So I can do this gap query. So this is my benchmark. I mean my reference. This is a decent split. I can split on this gap, but I want to insert this artificial split, which starts right at this time. There is also the possibility of splitting at artificial point. I will call this initial gap time. So I can just take this earliest split t and take timestamps. Earliest split I. So this is guaranteed to be larger than split t because this is upper bound. It must be larger. So if it's larger, then we are going to do this artificial split, otherwise we're going to follow this path. And here we will define those trees differently. So the left window, the left display is going to start here and it's going to end at not here, but let's split t. And the end is going to be earliest split I. The issue? I think this should give times, right? Yeah. Right is going to start at timestamp of this. It's going to end at entity. That's good. Yep. That should produce a nicer division of displays and more gaps. So now we should be able to have a display per gap, per point, per data point. Yeah, looks like it's working. And see that it's breaking them pretty well. It's maybe suboptimal that this vertical movement was broken, but otherwise find this next one. Right, left, right, left, right, left. And we crashed. But cool, segment trees seem to be doing the job. Still some cleanups here to do. So I think on Monday we will be cleaning up this code. We should properly store this state. There is no point to rebuild the tree on every frame. We are doing this right now. This check could happen before we push a display onto the queue. I wonder if I zoom in all the way in. I want to see individual samples. Okay. Doesn't work that well yet. I still don't see like I said, individual samples. What could be happening here? So earliest split T will be here, latest split T will be, I don't know, here. So earliest split I will hit in this point. Latest split I also hit this point. Earliest split I will be this, latest will be also this, but then I will do -1. So this will give me the point, must belong to the next range. I think there are some possible... I think this algorithm should have some possible modifications where I allocate these plays to be around this point. Not necessarily to start at this point, but to surround it. Some values. Seems like I always have at least 2 values per display. Sometimes even 3. Okay, I can relax this to greater. Actually, no, if they are equal, then that would cause issues. Hey! Okay, this is laggy, but this is because this is a debug, I think, build. So we're trying to design a timeline view in a way which will intelligently divide a mouse trace into meaningful components. So when I have a mouse trace that does this zigzag, vertical, then horizontal, and then some like 8s, it will divide it like that. This is how it runs. It's laggy because it's the debug build. So this works, right? On high level, it works really nicely. Yeah. I just want it to work all the way down to, as I'm increasing zoom, I can see more and more kind of details. It breaks down the mouse trace into smaller chunks. But I want to be able to see a single event, a single signal that a mouse sends as a single display. As I'm zooming to the scale of... At the scale of 4 milliseconds, it becomes visible. I have 1, 2, 3 mouse points in this mouse trace, and they are drawn on a single very wide display. This final level of zooming, it's still something that I need to address this, but it's very tricky to address. I think that maybe I could place the displays slightly differently so that they start a little bit before and end a little bit after a point. So I would subtract half here, and I would add half of the length here. Analysis size, do I use this anywhere? I do not. Okay, this condition is going to stay. This is what allows us to zoom in very closely. So we are basically recomputing the whole layout for thousands of points on every frame. But we are doing this in this quick sortie way, where we can discard large chunks of the layout. So we're actually skipping a lot of work, thanks to those two ifs. Okay, this looks good. Still, this is slightly too conservative, but this only becomes a problem at very high zoom levels. So I'm finding this gap. I need to split them differently now. So the change that I've done, where I just add or subtract a small value, it only makes the outer displays a little bit wider than they were. So the first or last point now will have nicer edges. Yeah, essentially the last display can end a little bit later or start earlier. I should actually change this. Maybe instead of analysis, I should call this root. Okay, blah blah blah, I'm finding the gap. Kind of nice to have those displays directly under. I'm not going to play with this. So now it looks alright until I zoom in very, very closely. Then we suddenly stop splitting the displays. There's some zoom level where it just stops working. I cannot zoom in below 1 millisecond. So I'm finding this point and the difference from here to here. Earliest split eye is this one. Okay, I don't want to produce too skinny displays. I can put 0 here. Duration guard is minimum. So it's going to be some negative number. Okay, that's fine. Okay, so this line is what is causing problems. Actually, if it's smaller, this is is when we can do the query. Okay, this should be always positive. We are guaranteed to have a gap. And if the gap is large enough, we can find a nice gap using this technique. Okay, should be slightly better now. Or it will fall apart. I guess it's easy to tell by the length of this stream. It's kind of my favorite thing to do. Debugging those kind of issues. Zoom in, zoom in. Are we going to get one sample displays? Not quite, or maybe we do. I think there is a zero width display here, possibly. Yeah. I think when I'm doing this right, start T should be this minimum. Okay, zoom in, see individual samples. Yes, they are here. It's just sometimes we are showing them from the right, sometimes from the left. This is because of, I guess, our algorithm. I actually have an idea. I think if we do one more pass, we could potentially center those displays so that they wouldn't start on the right or left. Because the problem only happens for displays whose length is basically the minimum length. And I guess I can just shift them around to center them on the values. Some of them will move right, some of them will move left. Greater than right t plus right 2. So here I have a step that adds the display. So this is the range of points covered by the display. I mean, maybe let's store them out of first point. And last point. Okay, this is a hack to auto-center recenter the displays that very few points. Okay, and we can already see this here. This display it's already at minimum size, but it's recentered to cover those points precisely. And we crashed. I think that was just a renderer crash. It's probably not a new bug. It's probably some old bug. Looks very nice. I zoom in very, very closely. You should see that they will start showing individual points. Yeah, it looks nice that it can chunk the mouse path. So nice. It's actually everything I wanted. It's actually perfect. I mean, actually no, I want more. I want it to be even cooler. But this will have to come later. Yeah, efficiency. We shouldn't recompute everything every frame. It's silly to do that. I don't know why it works. It's nice, but should probably be more clever about it. The thing I really like is that now when I zoom in, there is not so much jumping around. It looks like the displays are actually splitting, not not kind of jumping all over the place. So I would say goal achieved. It looks like zooming. Alright, this is it for today. See you on Monday. Bye bye.